Have you ever looked up at the night sky and felt a profound sense of wonder, a feeling that we are part of something immeasurably vast and mysterious? We send our probes and our telescopes out into the black, listening for whispers from the cosmos, hoping for a sign that we are not alone. But what if a sign arrived, not as a faint radio signal, but as a physical messenger from another star system, a traveler that has journeyed for millions of years through the interstellar void? And what if, as this incredible visitor threaded its way through our own planetary neighborhood, the very institutions we trust to tell us about the universe fell silent? Right now, at this very moment, an object named 3I Atlas is hurtling through our solar system. It's not one of ours. Its journey didn't begin in the Kuiper Belt or the Oort cloud, the icy nurseries of our own comets. No, this traveler came from the deep, deep dark between the stars. It is, in the most literal sense of the word, an alien, moving at a staggering 61 kilometers per second, a speed so immense that our sun's gravity could never hope to capture it. It is on a one-way trip through our home. This isn't just another rock. It is only the third confirmed interstellar object humanity has ever had the privilege to witness. Just imagine that. In all of our history, across all the star charts and celestial observations, this is only the third time we've ever been able to point to a speck of light and say with certainty, that comes from another star. You would expect, wouldn't you, that such a monumental event would be front-page news? You'd imagine live press conferences from the National Aeronautics and Space Administration, breathless announcements, and a global community of scientists and citizens alike captivated by the spectacle. Yet, if you go looking for that, you will find an unnerving quiet. The European Space Agency has offered little more than a few technical blog posts, the kind of dry updates you'd expect for routine satellite maintenance. The National Aeronautics and Space Administration, usually a master of public engagement, has been strangely reserved, uploading data to archives with minimal fanfare. It's a paradox, isn't it? We are witnessing a moment of maximum celestial drama, met with minimum institutional noise. But the story gets stranger. As this cosmic voyager makes its historic pass by Mars, a trajectory that seems almost impossibly precise, hundreds of high-ranking defense officials were just summoned to an urgent, closed-door meeting at Quantico. The official purpose? Vague. The timing? Unsettling. Is there a connection? No one is saying. It could be a coincidence, a simple quirk of timing. But in a story this big, with stakes this high, can we afford to believe in coincidences? Here is what makes 3I Atlas so utterly captivating, and to some, deeply concerning. Its path isn't a random streak across the sky. It's threading the needle between worlds, almost as if it has an itinerary. It's passing Mars right now, in early October. In November, it will swing by Venus. In December, it will make a pass by our own home, Earth, before continuing its grand tour toward Jupiter next spring. One object, one trajectory, 4 planets. And as this cosmic ballet unfolds, the world's leading space institutions seem to have forgotten how to throw a press conference. And then there's a twist that feels like something out of a science fiction film. Right when 3I Atlas reaches perihelion, its closest and most heated approach to our sun, the moment it will be most active and reveal its deepest secrets, our view from Earth will be completely cut off. For weeks, the sun's own glare will blind our most powerful telescopes. It's a perfect solar conjunction, a geometric blackout that couldn't be more precisely timed if it were planned. During this critical window, our only eyes will be the orbiters we have stationed around Mars. We will be almost completely blind. So, what will we discover when we can finally see it again in December? The answer might depend entirely on the questions we are willing to ask right now. The silence from the major players isn't just random static. It feels deliberate, selective. It creates a vacuum, and into that vacuum, speculation, curiosity, and a little bit of fear are rushing in. We are on a journey to understand not just what 3I Atlas is, but why its arrival is being met with such a profound and unsettling quiet. Let's follow the breadcrumbs, separate the hard science from the rampant speculation, and find out why. This isn't just a story about a comet. This is a story about the gaps in our knowledge, the gaps in our observations, and the unnerving gap between what is happening up there and what we are being told down here. Think about it for a moment. A visitor from an alien solar system, after a pilgrimage that may have lasted eons, is now close enough for us to study. This is not some distant curiosity passing billions of miles away. It is right here, in our celestial backyard. The implications are staggering. Every photon of light captured from this object is a page from a book written in a different cosmic language. Its chemistry tells us about the building blocks of a solar system that isn't ours. Its trajectory holds clues about the gravitational dynamics of its birthplace. This is our chance to touch the interstellar medium, to analyze a pristine artifact from another corner of the galaxy. And yet, the official channels are treating it with a calm that borders on indifference. Why? To understand the depth of this mystery, we need to appreciate just how special this moment is. The first interstellar visitor, 1I Aoumuwa, which shot through our system in 2017, was a complete enigma. We saw it only as it was leaving a faint, fast-moving point of light. It was strangely elongated, and it accelerated in a way that defied easy explanation, leading some, like the high-profile Harvard astronomer Avi Loeb, to famously suggest it could be an artifact of extraterrestrial technology. We had so little time, so little data. Aoumuwa was a ghost. The second visitor, 2I Borisov in 2019, was more familiar. It looked and behaved much like a comet from our own solar system, giving us a comforting, if less exciting, point of comparison. But 3I Atlas is different. We detected it early, on July 1st, 2025, thanks to the Atlas survey in Shul-E, a robotic system designed to be our planetary defense watchdog. Right away, its orbit screamed, "Not from around here." Its path was hyperbolic, an open-ended trajectory, proving it was not bound by our sun. By July 2nd, its status was official, designated C2025N1 by the Minor Planet Center. That little 3I in its name is a quiet testament to its significance. The third interstellar object ever confirmed. We have more time to study it, more powerful tools like the James Webb Space Telescope aimed in its direction, and a chance to get a much closer look. This should be a moment of triumph for astronomy, a celebration of our ability to detect and analyze such messengers. Instead, the narrative is being shaped by whispers and shadows. The data that has been quietly released is tantalizing. An update from the Hubble Space Telescope on August 7th gave us a sense of its size, or rather, our uncertainty. The nucleus, the solid core of the object, is wrapped in a glowing coma of gas and dust, making it impossible to see directly. Based on the coma's brightness, scientists estimate the nucleus is no more than 5.6 kilometers across, but it could be as small as a few hundred meters. That's a huge range with massive implications. A larger nucleus would be a substantial body, a mini-world of ice and rock. A smaller one would be more like a fragile rubble pile, barely holding itself together. We don't know which it is, a majestic iceberg or a delicate snowball. Then, on August 25th, the James Webb Space Telescope team dropped their bombshell, though they did so in the quietest way possible, by uploading a preprint paper to an online archive with little to no fanfare. This is where things get truly weird. The coma of 3I Atlas is overwhelmingly dominated by carbon dioxide. The ratio of CO2 to water is a staggering 8-to-1. To put that in perspective, that is not just unusual. It is almost unheard of. Comets in our solar system are water worlds. They are dirty snowballs where water ice is the king, the primary engine of their activity. 3I Atlas is different. It's more like a chunk of dry ice, fizzing with CO2. It's chemically alien. This isn't just a visitor from another star. It's a visitor built from a completely different recipe. As if that weren't enough, the timeline of observation adds another layer of intrigue. In early October, the European Space Agency's orbiters at Mars, the Mars Express and the ExoMars Trace Gas Orbiter, are perfectly positioned to study the object as it makes its closest pass to the red planet. They will give us our best, most detailed look at its chemistry in real time. But then, the blackout. Just as 3I Atlas gets to the most interesting part of its journey, its close swing around the sun, Earth's view will be blocked. For weeks, we will be flying blind. We will have to rely on the data trickling back from Mars and wait. We are in a race against time and geometry, trying to piece together the puzzle of this enigmatic traveler before it disappears back into the interstellar night, taking its secrets with it. This is the situation. A scientifically priceless object, a series of bizarre anomalies, an approaching observational blackout, and a wall of institutional reticence. The story of 3I Atlas is just beginning, and it's already one of the most compelling mysteries of our time. What do you think is going on here? Are we witnessing a series of incredible, but ultimately natural coincidences? Or is there a deeper story waiting to be uncovered, hidden in the silence? So, how do we begin to unravel a mystery of this magnitude? When faced with a story that feels almost too incredible to be true, the only place to start is with the cold, hard facts. Before we can explore the shadows, we must first map the solid ground of what we demonstrably know. We need to build a baseline reality, a foundation of undisputed numbers and observations. Because it's within the cracks of this foundation that the most interesting questions live. Let's become cosmic detectives for a moment and examine the evidence piece by piece. Where does the official record begin? And more importantly, where does it start to feel incomplete? Our story begins not in the hallowed halls of a major space agency, but with a silent, robotic guardian. On the night of July 1st, 2025, a set of automated eyes in Chile, part of the Atlas network, flagged something unusual. Atlas stands for Asteroid Terrestrial Impact Last Alert System. Think of it as our planet's tripwire, a network of telescopes scanning the skies every night, looking for anything that moves, anything that could pose a threat to us here on Earth. It's a sentinel, designed to give us a fighting chance against a potential impact. On this night, Atlas did its job perfectly. It spotted a faint point of light, moving in a way that didn't quite fit. It was an outsider. The system sent out an alert, and within hours, the astronomical community began to stir. The alert went to the Minor Planets Center, the official international clearinghouse for all things cometary and asteroidal. This is the world's switchboard operator for the solar system. They take observations from observatories big and small all over the globe, run the complex orbital calculations, and deliver the final verdict. Within a mere 24 hours, they had their answer. The calculations were undeniable. This object wasn't just on an unusual path. It was on a hyperbolic trajectory. Now, that sounds technical, but what it means is both simple and profound. Imagine throwing a ball up in the air. Gravity pulls it back down. That's a closed orbit. Even the comets from the farthest reaches of our own solar system are still on unimaginably long, but ultimately closed orbits. They are bound to our sun. A hyperbolic trajectory, with an orbital eccentricity greater than 1, is the mathematical equivalent of a one-way ticket out of here. This object was moving so fast, carrying so much energy from its interstellar journey, that it was merely skimming through our sun's gravity, well before being flung back out into the void. It wasn't visiting. It was just passing through. And so, it received its official name, 3I Atlas, with the formal designation C2025N1. Let's break that down because it's like reading a cosmic license plate. The C tells us it's cometary. It has a visible coma, a fuzzy halo of gas and dust, meaning it's an active, outgassing body, not just a dead rock. The 2025N1 is a timestamp telling us when it was discovered. But the most important part of that name is 3I. It's a quiet declaration of history in the making. The I stands for interstellar, and the 3 means it is only the third such object ever to be confirmed by humanity. This isn't just another comet. It's a member of an incredibly exclusive club. The numbers associated with its journey are just as mind-boggling. It entered our awareness, traveling at approximately 61 kilometers per second relative to the Sun. To give you some context, the fastest spacecraft ever built by humans, the Parker Solar Probe, reaches its top speed by falling towards the Sun, using gravity like a slingshot. 3I Atlas arrived with that incredible velocity already packed in its luggage, a momentum carried across countless millennia from its home star. The geometry of its path is what gives the story its narrative punch. On October 3rd, it makes its closest pass of Mars, a flyby at about 30 million kilometers. That might sound like a huge distance. It is about 80 times the distance from the Earth to the Moon, but in the vast emptiness of space, for an interstellar object that is threading the needle. It's not on a collision course, not even remotely dangerous, but it's close enough for the instruments we have orbiting Mars to get a fantastic look. Let's be absolutely clear on this point, because the last thing anyone needs is doomsday panic. 3I Atlas poses zero hazard to our planet. This is not an impact scenario. It is a once-in-a-generation observational opportunity. After its Mars encounter, it continues its dive inward, reaching perihelion, its closest point to the Sun, on October 30th, at a safe distance well outside Earth's orbit. Its later pass of our planet is even more distant. This is a scientific goldmine, not a threat. So we know its origin, we know its path, but what is it? What is this visitor made of? Our first real clue came from the venerable Hubble Space Telescope. On August 7th, Hubble stared intently at the faint visitor and gave us our first constraint on its size. The problem is, the nucleus itself, the solid heart of the comet, is too small and too far away to be seen directly. It is like trying to spot a piece of coal in the middle of a swirling cloud of smoke from miles away. All Hubble can do is measure the brightness of the smoke, the coma, and from that, model how big the piece of coal must be to produce it. The answer? It's probably no bigger than 5.6 kilometers across, but it could be as tiny as a few hundred meters. Think about the massive difference between those two possibilities. A 5-kilometer nucleus is a respectable comet, a mountain of ice with its own significant mass. A nucleus of only a few hundred meters is more like a cosmic rubble pile, a fragile collection of ice and dust barely held together, vulnerable to being torn apart by the sun's heat and gravitational forces. Is it a battleship or a canoe? Right now, we simply don't know. The heart of 3I Atlas remains an unresolved mystery, a tiny dark seed wrapped in a beautiful, glowing shroud. But if Hubble gave us the ghost's dimensions, it was the James Webb Space Telescope, our infrared monster, that told us what the ghost is made of. And this is where the story pivots from unusual to genuinely strange. In late August, the Webb turned its powerful spectroscopic instruments towards 3I Atlas, and the results, posted quietly as a preprint paper, were stunning. The data revealed a coma utterly dominated by carbon dioxide. For every 1 part water, there were 8 parts carbon dioxide. This is, to put it mildly, bizarre. It's like finding a creature from the deep ocean that breathes not water, but fire. Our solar system's comets are fundamentally water-based. They are born from water ice. 3I Atlas is not. It's a carbon dioxide entity, a fizzy, bubbling thing made of dry ice. This single chemical fingerprint is perhaps the most compelling piece of evidence we have that this object was born in a radically different environment than our own, a colder, more carbon-rich corner of the galaxy. This brings us to our forward observation post, Mars. The European Space Agency, which operates two sophisticated orbiters around the red planet, announced they would be conducting an observation campaign during the October 3rd flyby. Their instruments, designed to sniff out trace gases in the Martian atmosphere, are perfectly suited to analyze the chemical makeup of the comet's coma in real time. This is our best chance to get a dynamic, evolving picture of this object as it heats up. It's a critical window of observation because of what comes next, the great observational blackout. As 3I Atlas swings towards the sun in late October, from our vantage point on Earth, it will disappear into the sun's blinding glare. This solar conjunction means our ground-based telescopes and even our space telescopes in Earth's orbit will be unable to see it. Just as things get most interesting, just as the comet is getting its maximum dose of solar radiation, we go blind. And this is where the cracks in the public record begin to appear. These aren't scientific contradictions, but narrative gaps, omissions and oddities in communication that create a perception of silence. First, there's the tone. Compare the way agencies are handling this to the media events they staged for the Perseverance rover landing or the DART asteroid impact. Those were celebrations of science, complete with live streams, countdown clocks, and public hype. 3I Atlas, arguably a more profound and mysterious event, is getting dry, technical blog posts. It's information, yes, but it's not showtime. It feels restrained, almost bureaucratic. Second, the data itself is scattered. To get the full picture of what's happening, you have to become a digital detective, piecing together information from the Minor Planet Center from NASA's, Hubble pages from the preprint server where the web data was posted, and from the European Space Agency's Mars mission pages. There's no central hub, no everything you need to know about 3I Atlas landing page. This fragmentation means that for the casual observer, the information is hard to find. And when information requires work, the perception of silence grows. Third, and perhaps most importantly, is the media asymmetry. Reputable science outlets have covered 3I Atlas, but their headlines are measured and cautious. New interstellar visitor detected. Meanwhile, the more speculative takes. Is this an alien probe? Why is NASA hiding 3I Atlas? Are designed to go viral. They travel faster and farther on social media because mystery is more shareable than caution. A low-drama official communication strategy combined with a high-drama celestial event creates a perfect storm for conspiracy and speculation. The absence of spectacle is being read by many as intentional suppression, when it may just be the culture of science clashing with the speed of social media. This is the landscape of our mystery. We have a set of hard, fascinating facts about an object that is challenging our understanding of how solar systems form. But these facts are being delivered in a fragmented, low-key way that creates a narrative vacuum. And into that vacuum, a much more dramatic story is being written. A story of secrets, silence, and a strange visitor whose intentions we cannot yet fathom. The official story is scientifically sound, but narratively weak. The speculative story is narratively compelling, but scientifically baseless. The truth, as always, likely lies somewhere in between, hidden in the data that is slowly, quietly being collected. The real question is, what other weirdness is lurking in that data? What anomalies are the scientists whispering about, even if they aren't yet shouting about them from the rooftops? Let's delve into the truly strange behavior of 3I Atlas and explore the anomalies that make this object so much more than just a chemically unusual comet. We've established the facts, the official story of 3I Atlas, but that's like reading the blueprint of an old house. You can see the layout, the dimensions, the materials. But the blueprints don't tell you about the strange creaks in the floorboards at midnight, the cold spots in the hallway, or the faint whispers you hear when the wind blows just right. To truly understand the house, you have to step inside and listen to its secrets. Now we move beyond the simple facts and into the genuinely strange, the data-backed anomalies that are making scientists lean forward in their chairs and whisper, "That's odd." This is where we separate the unusual from the truly bizarre. And this is where the mystery of 3I Atlas deepens. Let's start with its chemical soul, because that's where the evidence is richest, and the story is most compelling. Remember that bombshell from the James Webb Space Telescope? An 8-to-1 ratio of carbon dioxide to water. I want you to truly absorb how remarkable that is. Imagine exploring a new continent on Earth and discovering that all the life there is based not on carbon, but on silicon. It would rewrite the rules of biology. That's the scale of weirdness we're talking about here, but for cometary science. Comets born in our solar system, whether from the nearby Kuiper Belt or the distant frozen Oort cloud, are fundamentally defined by water. Water ice is the engine of their existence. As they approach the sun, that water ice turns to gas, creating the beautiful coma and tail we associate with comets. Other ices are present, sure, carbon dioxide, carbon monoxide, but they are almost always the supporting actors, present in amounts of maybe 10 to 30% of the water. They are the seasoning, not the main course. 3I Atlas flips the entire cookbook upside down. It's a comet that runs on carbon dioxide. It's like a person who breathes CO2 and exhales oxygen biologically backward, thermodynamically confusing, and demanding an explanation. So, what could possibly explain this? Scientists, in their quiet, methodical way, have proposed a few fascinating possibilities. The first is perhaps the most profound, that this is simply what comets look like where 3I Atlas was born. Just imagine a solar system formed around a different star, with a different chemical makeup, a different temperature gradient. In the protoplanetary disk of that alien sun, perhaps carbon dioxide ice was far more common or stable than water ice. What we are seeing isn't an anomaly. It's a genuine snapshot of alien chemistry. 3I Atlas isn't broken. It's just not from around here. It's a chemical postcard from an unknown star. Another, equally compelling idea is the layered nucleus hypothesis. What if the water is there, but it's hiding? Picture the comet's nucleus not as a uniform snowball, but as a kind of cosmic gobstopper with layers. The outer shell, exposed to the cold of interstellar space for millions of years, is made of highly volatile carbon dioxide, ice, and dust. But deeper inside, buried beneath that fizzy crust, lies a heart of good old-fashioned water ice. Carbon dioxide turns to gas at much lower temperatures than water. So, as 3I Atlas makes its journey towards our sun, the outer CO2 layer is the first thing to cook off. We're seeing the fizz before the steam. What's the prediction here? It's a beautiful piece of testable science. If this hypothesis is correct, then after 3I Atlas swings around the sun at perihelion, when the solar heat has had time to penetrate deeper, we should start to see the water signal dramatically increase. The chemical signature should evolve before our very eyes. It's a beautiful theory, but only time and data from the other side of the blackout will tell. There's a third possibility, a middle ground between the other two. Perhaps the nucleus is just messy, not layered, but patchy. Multiple observers, from professional networks to skilled amateurs, have documented that 3I Atlas doesn't brighten smoothly. It flickers. It has little outbursts, sudden variations in brightness that suggest it's not outgassing in a steady, constant stream. Some have used the evocative language of a comet that is breathing or pulsing with activity. While that might sound like science fiction, the underlying data, the light curve variations, are very real. Now, this isn't completely unheard of. Comets can have jets. But the pattern for 3I Atlas seems more erratic, more dynamic than usual. One hypothesis is that the nucleus has a thin crust of dust. Gas pressure builds up beneath this crust until it suddenly cracks open in a violent outburst, releasing a plume of gas. Then, the vent might seal itself over, and the process repeats. It's a fascinating model of a dynamic, cracking, and breathing world, all driven by natural thermal physics. And what about the pictures? Some of the images captured by amateur astronomers show something that seems to defy the laws of physics. A tail, or a plume of material, that appears to be pointing towards the sun, not away from it. This sounds impossible, right? The solar wind and the pressure of sunlight are supposed to push dust and gas away from the sun, forming the classic comet tail. And they do. But what we're likely seeing is a spectacular optical illusion known as an anti-tail. Imagine a trail of breadcrumbs left along the comet's orbital path. These are larger dust grains that aren't easily pushed by the solar wind. If our viewing angle from Earth is just right, if we are looking at this trail of cosmic dust edge on, it can create the illusion that part of it is pointing towards the sun. A famous comet in 1957 had a spectacular anti-tail that baffled the public. So the sunward plume is probably a trick of geometry and perspective, not a sign of some exotic propulsion system. Probably, but it looks incredibly strange, and in a story like this, appearances matter. It adds another layer of visual weirdness to an already mysterious object. All of these anomalies, the chemistry, the behavior, the visuals are made more complicated by the fact that we still don't really know how big this thing is. Is it a 5.6-kilometer mountain of ice, or a few hundred-meter rubble pile? The difference is critical. Mass tells you how an object should behave, how resilient it is to heat, and how much its path can be altered by its own outgassing jets, acting like tiny, natural thrusters. Until we can pin down its mass, we're still dealing with a ghost. When you compare 3I Atlas to our previous interstellar visitor, 2I Borisov, the contrast is stark. Borisov felt familiar. It had some unusual chemistry, yes, but it was broadly within the family of comets we know. It was like meeting a cousin from another country. They might have a different accent, but you could still recognize the family resemblance. 3I Atlas feels like something else entirely. The extreme CO2 dominance, the pulsing activity, the deceptive visuals, it's pushing the boundaries of what we even consider a normal comet to be. It is almost certainly a natural object, born of star stuff and ice, just like the comets in our own system. But it's a natural object that is testing the limits of our models and our imaginations. And that's before we even talk about its trajectory. The one thing that, more than any other, makes us look at this chain of events and wonder, what if its path through our solar system isn't random at all? What if it's almost convenient? This brings us to the question that hangs in the air, the one everyone wants to ask, but feels silly for even thinking. Is there any chance this thing is deliberate? All right, let's address the elephant in the room. It's the part of the story that sends a little shiver down the spine, the part that makes the jump from a fascinating scientific curiosity to a potential paradigm-shifting mystery. We're going to talk about the orbit of 3I Atlas, and as we do, we need to walk a very fine line. On one side is the dizzying abyss of wild speculation. On the other is the firm, but sometimes unsatisfying ground of scientific probability. Because this is where the sequence of events begins to feel less like a random cosmic occurrence and more like more like a mission. First, let's talk about its angle of approach. 3I Atlas is traveling in a retrograde orbit, meaning it's moving in the opposite direction to our planets. Think of our solar system as a racetrack, with all the planets speeding along in a counterclockwise direction. 3I Atlas has entered the track going clockwise. This in itself isn't particularly strange for an interstellar object. They can come from any random direction in the galaxy. But here is what is notable. Our solar system is incredibly flat. The planets orbit the sun in a thin disk called the ecliptic plane. You might expect a random visitor from interstellar space to slice through this plane at a steep angle, coming in from high above or deep below. The vast majority of random trajectories would do just that. But 3I Atlas is different. Its orbit is inclined only about 5 degrees from our ecliptic plane. It is almost perfectly coplanar. It is like a car merging onto a highway and aligning itself almost flawlessly with the lanes of traffic, except it's driving head-on into the flow. Why does this matter? Well, it just feels neat, too neat for some. Now, before we leap to conclusions, we have to acknowledge a powerful scientific caveat: selection bias. Where do we point our telescopes? We point them along the ecliptic plane because that's where all the action in our solar system is. That's where the asteroids are, where the comets are, where the planets are. We are constantly searching that thin strip of sky. So, it stands to reason that we are far more likely to discover an interstellar object that happens to be traveling through that plane, simply because that is where we are looking most often. It's the classic looking for your keys under the streetlight problem. You look there not because that's where you lost them, but because that's where the light is. So the seemingly perfect alignment of 3I Atlas' orbit might just be an artifact of how we search the sky. It's the most likely explanation. But what if it's not? Let us set aside the selection bias for a moment and just look at the grand tour this object is taking. On October 3rd, it flies by Mars at a distance of just 0.19 astronomical units. That is, as we've said, incredibly close for a random interstellar passerby. It's close enough to get a good look at the Martian environment, to sample its thin atmosphere, its magnetic field, the dust that surrounds it. If you were a robotic probe sent from another star to study the planets in our solar system, this is exactly the kind of flyby you might perform. You wouldn't need to enter orbit, which is incredibly costly in terms of energy and fuel. You would simply make a close pass to gather as much remote sensing data as possible before moving on to your next target. And it is moving on to the next target. After its Mars encounter, it continues its journey, reaching its closest point to the Sun on October 30th. This path keeps it in a perfect sweet spot close enough to the Sun for its ices to sublimate and reveal its chemical secrets, but far enough away to avoid being torn apart by tidal forces. It's the ideal observational window. Then, its trajectory takes it on a tour of the inner solar system. On November 3rd, it will pass Venus. On December 19th, it will make its closest approach to Earth. And then, as if for a grand finale, it will swing past the king of our solar system, Jupiter, in March of 2026. One object sequentially visiting Mars, Venus, Earth, and Jupiter. Do you see the pattern? Does that feel random to you? If you were to sit down at a mission control panel and design a grand tour flyby mission of our solar system, this is the kind of trajectory you might plot. You would use a single efficient path to encounter multiple high-value planetary targets in a logical sequence. Now, to be clear, a real mission would likely be optimized for even closer flybys and more specific scientific goals. But the general architecture of the journey, the sequential planetary encounters, it has the unmistakable feel of a mission profile. This is where we must be incredibly careful and introduce a concept called the base rate fallacy. This is a cognitive trap we all fall into. We see a pattern that looks meaningful, and we immediately assign significance to it, without stopping to consider how often that pattern might occur purely by chance. Yes, the path of 3I Atlas takes it near 4 major planets. But interstellar space is vast, and objects are constantly flying through our solar system on random trajectories. Given enough time, some of those random paths will, by sheer statistical luck, happen to align in a way that looks interesting. We don't notice the countless boring trajectories that miss everything. We only notice the one that hits the jackpot. It's like dealing a hand of cards. If you get a royal flush, you feel like something special has happened. But a royal flush is just one combination of cards out of millions. It's rare, but it's not impossible. It doesn't mean the deck was stacked. The trajectory of 3I Atlas could simply be our solar system's version of a royal flush, a beautiful, rare, but ultimately random alignment. This is the very same cognitive trap that ensnared many during the passage of Oumuamua. Oumuamua was weird. It was shaped like a cigar, and it accelerated away from the sun in a way we couldn't easily explain. Avi Loeb, the Harvard astronomer, famously proposed that it could be an artificial light sail, a thin, reflective probe being pushed by the pressure of sunlight. The mainstream explanation is that it was outgassing jets of gas that we just couldn't see. But the debate was never fully settled, because Oumuamua was gone before we could get a good enough look. It left us with a tantalizing and unanswered question. 3. iAtlas is giving us a much longer observation window, but it comes with its own set of ambiguities. The central question that scientists will be trying to answer in the coming months is this: will it exhibit non-gravitational accelerations that cannot be explained by its own outgassing? When a comet spews jets of gas, it's like a tiny, chaotic rocket engine. It gets pushed around. This is normal. But the push should be consistent with the gas we see. If you see a bright jet of CO2, you can calculate precisely how much thrust it should produce. If the comet's trajectory changes by that exact amount, then all is well. It's just a comet doing comet things. But what if the change is bigger? What if the acceleration is in the wrong direction? What if the object steers itself in a way that defies the physics of its own outgassing? That is when the puzzle deepens. That is when we would have a genuine, unexplained anomaly on our hands. The lesson from Oumuamua is to be very, very careful about drawing grand conclusions from sparse data. With 3 iAtlas, we will have much more data months of observations from multiple instruments. But we still won't get the one thing we truly want: a clear, resolved picture of the nucleus. We will be studying this object indirectly, through the light it reflects, the gas it emits, and the subtle wobbles in its path. It is like trying to understand a person by listening to their footsteps in a dark room and seeing the shadow they cast on the wall without ever seeing their face. So, is the trajectory of 3 iAtlas evidence of intent? The honest, scientific answer is no. The overwhelmingly most likely explanation is that we are witnessing a natural comet on a random interstellar journey that just happens to be a spectacular one. That is the null hypothesis, and it should be our starting point. And this is a very important, that the exotic hypothesis, the idea that something deliberate is going on here, is testable. We don't have to just wonder. We can measure. We can collect the data, and the data will either confirm the natural explanation or force us to confront something far more profound. And as if the cosmic timeline weren't strange enough, there's that other timeline, the one happening right here on Earth. The timing of that massive secret gathering of U.S. military leadership at Quantico, right as this interstellar drama is unfolding. Is that really just another random piece of the puzzle? Or is it a sign that the patterns we're seeing aren't just in the sky, but are also being drawn in the corridors of power? Let's explore that connection and ask what it would mean if the world's most powerful military was turning its eyes to the same strange visitor that has so captivated us. Let's shift our gaze from the cold, silent theater of space to the tense, whispered corridors of power here on Earth. Because the story of 3 iAtlas isn't just being written in the light of distant stars. It's also being written in the conspicuous silence of our own institutions. In late September of 2025, just as 3 iAtlas was making its critical approach towards Mars, an event took place that, in any other context, might have been a footnote in the news cycle. But in this context, it feels like a thunderclap. The entire senior leadership of the United States defense establishment were talking the Joint Chiefs of Staff, senior Pentagon officials, the kind of figures who command armies and shape global strategy, were summoned to Marine Corps Base Quantico for a meeting. This wasn't your typical weekly briefing or a scheduled conference. Multiple mainstream news outlets, including Reuters and Al Jazeera, described the gathering as unusually large, short notice, rare, and abrupt. The official purpose given to the press was so vague as to be almost meaningless. Strategic discussions about ongoing operations. It's the kind of sterile, boilerplate language designed to say nothing at all. When the White House press secretary was asked about it, the response was a swift downplaying of the event. Routine stuff. Nothing to see here. Defense leadership meets all the time, and that's true. They do. But the optics of this particular meeting, the sheer size of it, the suddenness, the wall of secrecy around its agenda, all of this combined to create a powerful perception of urgency. And urgency, especially secret urgency, is a breeding ground for speculation. So, here's the pattern that thousands of people around the world are now matching. On one hand, a mysterious interstellar object is performing a series of precise flybys of our planets. On the other hand, the entire military brass of a superpower is convening in secret. Is it a coincidence, or is it coordination? Now I need to be absolutely, crystal clear about this. There is zero public evidence connecting the Quantico meeting to 3I Atlas. None. Not a single leaked memo. Not one whistleblower statement. No on-the-record comment from any official linking these two events. If you are going to draw a line between Quantico and the comet, you are doing so based on one thing and one thing alone: timing. And in the world of evidence, timing is the weakest link. It's circumstantial at best, and purely coincidental at worst. But let's also be intellectually honest and acknowledge why people are making that connection. It's not an irrational leap. It's just not an evidential one. The concept of space domain awareness is a core pillar of modern military strategy. The United States Space Force exists for this very reason: to track objects in orbit and beyond, to understand potential threats and anomalies, and to coordinate with civilian agencies like the National Aeronautics and Space Administration. It is their job to watch the skies. If a truly unusual object were to enter our solar system, behaving in ways that were difficult to explain, you can be certain it would warrant a high-level security briefing. Let's just play out the what-if scenario for a moment. What would it mean if the Quantico meeting was about 3I Atlas? You would need to coordinate a massive observation campaign across both military and civilian assets, ground-based radar systems, classified space-based telescopes, signals intelligence platforms. You need to get all the key decision-makers in one room to align priorities. Who points what, where, and when? Who gets access to the raw data? And most critically, how do you manage the public communication of your findings without compromising highly sensitive national security capabilities? That is precisely the kind of complex, high-stakes coordination that demands a face-to-face meeting of senior leadership. Then there's the information control angle. Imagine for a moment that there was genuine uncertainty about what 3I Atlas is. Not a certainty that it's alien, but a lack of certainty that it's natural. If you didn't want to cause a global panic or create a complicated diplomatic situation before you had definitive answers, what would you do? You would establish very clear guidelines for what information gets shared publicly and what stays internal until it can be verified. This isn't necessarily a sinister cover-up. It's risk management. It's the difference between a responsible statement, like, "We are tracking an unusual object and are gathering more data," and a panicked one like, "We don't know what this thing is, and we're concerned." The first is prudent. The second ignites chaos. But there are also limits to this line of thinking. A defensive posture against 3I Atlas makes absolutely no sense. We know its trajectory with incredible precision, and it is not a threat to Earth. And even if it were headed our way, we currently have no technology that could deflect or destroy an object of its potential size, moving at that incredible speed. The DART mission was a stunning success, proving we can nudge a small asteroid with years of careful planning. But an interstellar object moving at 61 kilometers per second is a completely different beast. So if Quantico was about 3I Atlas, it wouldn't have been a meeting about defense. It would have been a meeting about observation and information control. There's also the signals intelligence aspect. This is where the speculation gets really interesting. If 3I Atlas were transmitting any kind of artificial radio signals, or even exhibiting unambiguous signs of a propulsion system, that is a secret that would be almost impossible to keep. The network of modern astronomy is too distributed, too international, and too open. There are thousands of professional and amateur radio astronomers with dishes pointed at the sky. The SETI, Search for Extraterrestrial Intelligence Community, would be buzzing with activity. The fact that the airwaves are silent, that there are no urgent calls for radio telescopes to coordinate observations of this object, tells us something important. It tells us that if there is anything strange about 3I Atlas, it is not announcing its presence through the electromagnetic spectrum. It is a silent traveler. Of course, we must also consider the mundane explanations for the Quantico meeting, because they are almost certainly the correct ones. Late September is the end of the fiscal year for the U.S. government. It's a time of intense bureaucratic activity, where budgets are finalized and strategic priorities for the coming year are set. A large gathering for planning is not just normal. It's practically an annual tradition. Beyond that, the world is a complex place. Geopolitical tensions in multiple theaters around the globe require constant coordination and contingency planning. A meeting of the Joint Chiefs could very well have been about conventional military readiness, having nothing whatsoever to do with the heavens. These explanations are less exciting, but they are far more probable. So why even include Quantico in this narrative? Because to ignore, it would be to ignore a massive part of the story that is unfolding in the public consciousness. It would be dishonest to pretend the elephant isn't in the room. The optics of the situation, the timing, the secrecy, the institutional silence from both the military and the civilian space agencies have created a powerful perception of a connection, whether or not a real one exists. This is the responsible way to frame it. The Quantico meeting happened. 3I Atlas is happening. The two events are happening at the same time, but they are, as far as we know from all available evidence, completely disconnected. If a concrete link is ever revealed, we will re-evaluate. But until then, we must treat them as two separate stories occupying the same moment in time. But here is why the narrative of a connection will not die. The absence of clear information from official sources creates a vacuum, and human nature abhors a vacuum. We fill it with patterns, with speculation, with stories. When the National Aeronautics and Space Administration gives you blog posts instead of a press conference, when the military convenes in secret and says, "Nothing to see here," and when social media is ablaze with connections that the mainstream media won't make, the narrative takes on a life of its own, and that narrative has consequences. It shapes public trust, it influences how we view our institutions, and it determines how seriously we take the next interstellar visitor or the next unexplained aerial phenomenon. This story isn't just about what 3I Atlas is. It's about who gets to define what it is, and what happens when the official story is too slow, too cautious, and too quiet for the speed at which questions now travel. And into that gap, a new generation of observers is stepping forward. The amateurs, the independents, the contrarians, the ones who are keeping this story alive. In the golden age of astronomy, the story of the cosmos was told by a select few. It was a tale written by men with access to colossal telescopes perched on remote mountaintops, gatekeepers of the heavens. But that age is over. We are living in a revolutionary new era, a time when the tools of discovery have been democratized. The story of the universe is no longer a lecture delivered from a podium. It's a global conversation, happening in real time, driven by a decentralized network of passionate observers. And in the story of 3 Atlas, these watchers in the dark, the amateur astronomers, the independent networks, the citizen scientists, have become the frontline correspondents, broadcasting from the edge of the unknown, while the institutional giants draft their carefully worded press releases. Think about what it takes to make a meaningful astronomical observation today. You don't necessarily need a billion-dollar budget anymore. You need a good camera, a steady robotic mount to track the stars, and access to dark skies or the clever software that allows you to cut through the light pollution of our cities. The barrier to entry has crumbled. Smart telescopes that can automatically align themselves, identify celestial objects from star patterns, and track them with precision now cost less than a used car. The sophisticated software needed to stack and process images is often free. The complex calculators that plot orbital mechanics are available online to anyone with a curious mind. This means that the people who are often first to document something new, something strange, are not the ones with government badges. They are the ones with a passion for the night sky and a decent internet connection. A perfect example is the Las Cumbres Observatory network. This isn't one observatory. It's a global web of robotic telescopes spread across the planet, working in concert. It's a professional-grade network, but it also provides access to advanced amateurs who can propose and run their own observation projects. When 3I Atlas was first confirmed, the instruments of Las Cumbres were among the very first to be trained on it, beginning a continuous 24/7 monitoring campaign. Almost immediately, images began appearing online not as polished NASA press releases, but as raw data dumps. Stacks of long exposure frames, beautiful time-lapse sequences showing the comet's stately glide against the backdrop of distant stars. These weren't filtered through a public relations department. This was pure, unadulterated data, shared by observers who were excited about what they were seeing. And what were they seeing? Some of those images gave us our first clear look at the structure of the coma, the glowing gas cloud. Some of them captured that faint, ghostly sunward plume, that optical illusion of an anti-tail we talked about. And some of them revealed the subtle brightness variations, the flickering pulse that hinted at the comet's erratic, outgassing heart. But they also showed other things. The telltale streaks of cosmic rays hitting the camera sensor, slight errors in tracking, the digital artifacts that can be created when stacking images. This is where the signal-to-noise problem begins. In this democratized age of astronomy, not every image is created equal. Not every observer uses the same calibration techniques. Not every analysis is scientifically rigorous. So when someone posts a spectacular image of 3I Atlas with a dramatic, flaring tail, you have to learn to ask the right questions. Is that feature real? Or is it a processing artifact? What filters were used? What were the sky conditions like? Is this a single snapshot or a composite of many images? This is why knowing where to look for reliable information is so crucial. If you want the vetted, trustworthy data, you go to the sources. The Minor Planet Center publishes official circulars with astrometric measurements, the precise position of the object submitted by observatories all over the world. These are cross-checked and verified. You go to JPL's Horizon system, which provides the official ephemeris, the predicted path and velocity of the object, updated constantly as new data comes in. These are the gold standards. Then there's the world of preprints. Servers like ArcSiv are where professional astronomers post their research papers before they veg on through the months-long process of formal peer review. This is absolutely vital for a fast-moving story like this one. The James Webb Space Telescope results we've been discussing, that was a preprint. It wasn't officially peer-reviewed yet, but it was authored by the mission's own team members, the people who built and operate the instrument. That gives it an immense amount of credibility. It's not gospel, but it's as close as you can get in real-time science. And then there's the noise. The unattributed screenshots on social media. The breathless claims of a giant nucleus based on a simple misreading of a brightness measurement. The YouTube videos with ominous music and no sources cited. These spread like wildfire, not because they are true, but because they are emotionally resonant. They tap into the narrative that people want to believe. Here, as a link to the Minor Planet Center's latest astrometric data, just doesn't have the same viral kick. Let's talk for a moment about some of the visual gotchas, because this is where so much misunderstanding happens. That anti-tail, the sunward spike, is a perfect example. You're looking at a three-dimensional object, a comet with a cloud of dust around it, traveling along a specific path in space, but you're seeing it projected onto the flat, two-dimensional screen of the sky. Depending on your viewing angle, that geometry can play tricks on your eyes. The dust tail can appear to curve, to bend, or even to point in a direction that seems physically impossible. To truly understand what you're seeing, you need to know the geometry of the situation, the angle between the sun, the comet, and you, the observer. You need to model the dust dynamics in 3 dimensions. Or you can just look at it, say, "Wow, that's weird," and post it online without context. Guess which one happens more often? This is why the coordinated amateur campaigns are so incredibly valuable. These aren't just casual sky watchers. These are networks of skilled observers who are doing real, publishable science. They are taking images on the same nights, using the same filters, and meticulously calibrating their data to build up light curves that track the comet's brightness over time with incredible precision. They are stacking hundreds of images to beat the noise and reveal the faintest details. This is systematic, methodical work, and it's providing a crucial, continuous stream of data that complements the snapshots taken by the big professional telescopes. But even this incredible work faces the amplification problem. A careful, nuanced analysis that concludes, we see a rotational period of approximately 14 hours with episodic brightening, consistent with localized outgassing jets, doesn't make headlines. A sensationalist interpretation that says, comet behaving erratically, possible alien probe, goes viral in an instant. Once that happens, the original signal of careful science, it's buried under an avalanche of noise. The correction never travels as fast or as far as the initial claim. Here's a prediction worth making. As we enter the great observational blackout, when Earth-based telescopes can no longer see 3-eye Atlas, the information vacuum will be at its deepest. And that is when you should expect to see more leaked images, supposedly from the Mars orbiters. Someone will post a grainy, dramatic picture online, claiming it's from the Mars Express, and that it shows something incredible, something anomalous. Before you believe it, you have to ask the hard questions. Does it have the official metadata? Is there a mission timestamp? Does the image resolution match the known capabilities of the instrument? Has the European Space Agency confirmed its authenticity? The chances are overwhelmingly high that it will be a fake or a misattributed image or a real image that has been misinterpreted. In a time of information scarcity, the bar for evidence needs to be higher, not lower. So, for those of us trying to follow this story responsibly, what's the takeaway? Stick to the sources with names attached. Follow the official updates, even if they are slow and dry. If someone makes a dramatic claim, ask to see their data. Ask for their methodology. If their finding is real, it will be reproducible by other observers. If it's just noise, it will remain an outlier. And remember this crucial truth. In science, spectacular doesn't always mean accurate. Sometimes, the most important discoveries are hidden in the most boring-looking data, the precise measurement of a position, the subtle shift in a spectral line, the null result that definitively rules out an exotic hypothesis. Science progresses by eliminating possibilities just as much as by confirming them. But this all brings us back to the central question. Why are the institutions being so quiet in the first place? Is it purely scientific caution, or is there another dimension to this story, a dimension of security that we're not being shown? Let's dig into that. So we arrive at the heart of perceived mystery, the question that fuels so much of the speculation and intrigue. Why the quiet? Why isn't the arrival of 3-eye Atlas the most exotic, chemically strange, And fascinating interstellar visitor, we've ever had the chance to study being met with a global celebration of science. Why isn't the National Aeronautics and Space Administration holding daily press briefings? Why isn't there a live public feed from the Hubble, a countdown clock to the Mars flyby? Why does it feel like this incredible celestial event is being treated with the muted enthusiasm of a routine software update? To find the answer, we have to look past the conspiracy theories and delve into the complex, often competing, cultures of science and security. Let's start with the most likely and most mundane explanation: the deeply ingrained culture of scientific caution. Organizations like the National Aeronautics and Space Administration and the European Space Agency have long institutional memories. They remember, with a collective wince, every time a sensational discovery was announced to the world, only to be later retracted in embarrassment. They remember the faster-than-light neutrinos from CERN in 2011, a groundbreaking discovery that would have rewritten physics, which turned out to be the result of a single loose fiber optic cable. They remember the announcement of arsenic-based life in Mono Lake, a claim that electrified the world, which was later shown to be the result of contaminated lab samples. These aren't just mistakes. They are institutional scars. They breed a profound sense of error aversion. The unwritten rule is simple. Before you announce something extraordinary, you must have extraordinary evidence. And extraordinary evidence takes time. Think about what it takes to be sure about an object like 3I Atlas. You don't just take one picture. You need observations over weeks and months to precisely characterize its orbit and look for those tiny, non-gravitational accelerations. You need to meticulously rule out every possible source of error instrumental glitches, atmospheric distortions, contamination from a background star. You have to fit your data to complex models, and those models require a long arc of data from both before and after its closest approach to the Sun. You can't fit a complex curve with just 2 or 3 data points. You need dozens or hundreds. And even then, every measurement, every conclusion comes with error bars, with uncertainties. The fundamental instinct of the scientific institution is to wait to gather more data, to let the rigorous, often brutally critical process of peer review do its job before you stand up in front of the world and make a bold claim. Then there's the simple, unglamorous reality of bureaucracy. The public information officers at these agencies don't just fire off a tweet whenever they feel like it. A single, simple blog post might have to go through 5 or 6 rounds of review. It has to be vetted by the mission scientists to ensure accuracy, by the legal team to ensure it doesn't violate any agreements, by international partners to ensure a coordinated message. They are painstakingly careful with their language, making sure not to say anything that could be misinterpreted or that might accidentally reveal a sensitive, technological capability of one of their instruments. This isn't a sinister conspiracy of suppression. It's the slow, grinding, and frustrating price of being a massive, multi-stakeholder organization. It's bureaucracy. And frankly, they have communicated about 3I Atlas. They have posted updates. They have shared the Hubble results. They have linked to the James Webb Space Telescope preprint. It's just that their communication style isn't Showtime. It's not a blockbuster movie trailer. And maybe, just maybe, that's appropriate. Because right now, we don't actually know for sure if there is anything truly extraordinary happening here. We know it's interesting. We know it's scientifically valuable. We know it's worth studying intensely. But interesting doesn't always translate to press conference worthy, especially when the most interesting parts of the story are still wrapped in uncertainty. Now, let's put on a different hat. Let's move from the documented culture of science to the more speculative and much murkier culture of security. Space domain awareness, as we've discussed, is a very real thing. The U.S. Space Force and its international counterparts are constantly monitoring the space around our planet. They track active satellites, defunct satellites, chunks of space debris, and near-Earth asteroids. Their job is to maintain a clear picture of anything that could pose a threat or simply be out of the ordinary. An unusual object entering the solar system on a peculiar trajectory would absolutely get flagged. Not necessarily because it's seen as a threat, but simply because it's an anomaly. And in the world of security, all anomalies get attention until they can be explained. It is crucial to state this again. There is no public indication that 3I Atlas has triggered any kind of defense posture. We have no statements from the Space Force, no leaks from congressional briefings, nothing. In fact, the very openness of the scientific data the public preprints, the Hubble posts, the European Space Agency's observation plans, argues against a tight security lockdown. If this were being treated as a classified event, the information control would likely be far more total. But here is where the water gets murky. The absence of evidence is not evidence of absence. Just because we do and see signs of security involvement doesn't mean it isn't happening behind the scenes. And this is the fertile ground where speculation lives in the gap between what is observable and what might be happening just beyond our view. If there were a security dimension to this, what would it look like? It probably wouldn't be overt. It would be subtle. It might involve classified sensors, perhaps spy satellites or ground-based, military radar taking their own measurements that do and get shared with the public. It might involve a quiet coordination between civilian and military tracking assets. It could even involve gentle restrictions on what mission scientists are allowed to say in public, not because the data itself is classified, but because the methods and technologies used to collect it are. The challenge for us, as outside observers, is that this kind of low-key security involvement would be almost indistinguishable from normal, everyday operations. Civilian and military space agencies coordinate all the time. The National Aeronautics and Space Administration shares tracking data with the Space Force as a matter of course. The technical capabilities of our most advanced instruments are often sensitive. It's a complex web of overlapping interests, and the bureaucratic choke points alone are enough to slow everything down. Imagine needing to get sign-off from the National Aeronautics and Space Administration, the European Space Agency, the National Science Foundation, and the Department of Defense before you can release a single statement. You're going to end up with one of two things. Either a bland consensus-driven statement that satisfies everyone but excites no one, or you're going to wait until the data is so overwhelming that it forces a single undeniable conclusion. Here is another speculative hypothesis to consider. What if the cautious language being used is a deliberate strategy? What if officials are scrubbing their communications of any language that frames the object's actions with intent, at least until they have the post-perihelion data in hand? Think about the difference. To say the object is making a close pass of Mars is a simple statement of fact. To say the object is targeting Mars is a loaded phrase. It implies agency, deliberation, and design. If you don't yet know which framing is correct, you stick with the neutral, scientific one until the data resolves the ambiguity. It is a way of managing the narrative and avoiding the risk of being wrong on a cosmic scale. This brings us to the most powerful argument for the institutional quiet. What if it's a form of strategic silence designed to bridge the observational blackout? If you're an agency leader and you know you're about to lose sight of this object for several weeks, why would you create a huge public expectation for real-time updates? You would be setting yourself up for failure. It's far more prudent to stay quiet. Let your assets at Mars collect their precious data. Wait for the sun's glare to clear, and then, once you have the full picture, release a comprehensive analysis. That way, you avoid the trap of trying to interpret incomplete, real-time data and potentially having to walk back your statements later. The takeaway from all of this is that the absence of drama does not equal the absence of data. In fact, it might just mean the opposite. It could be that there is so much data being collected, so much analysis being done behind the scenes, that the institutions are simply focused on doing the science and public communication has taken a back seat. If you really want to know what's happening, the press releases are the last place you should look. The real story is being written in the preprints, in the mission logbooks, and in the observation schedules. But here is the beautiful irony. While Earth goes blind, while the institutions wait, we have a forward operating base. We have robotic eyes in orbit around another world. And for a few critical days in October, Mars will become the most important vantage point in the entire solar system. Let's go there now. As the curtain of solar glare begins to fall for us here on Earth, the stage is just being set for the main event hundreds of millions of kilometers away. For a few crucial days, from October 1st through the 7th, the story of 3I Atlas will be told not from our planet, but from the next one over. Mars, the red world of our myths and our future ambitions, is about to become our frontline observatory, our sentinel in the dark. While our own telescopes are forced to turn away, two sophisticated European Space Agency spacecraft already in orbit around Mars will have a front-row seat to the flyby. This is not a mission that was planned. It is a fortunate accident of celestial geometry, an opportunistic moment to turn instruments designed to study a planet towards a visitor from the stars. The two spacecraft are the Mars Express, a seasoned veteran that has been orbiting the red planet since 2003, and the ExoMars Trace Gas Orbiter, TGO, a newer, more sensitive probe that arrived in 2016. Both were built with one primary goal in mind: to study Mars. They are designed to analyze its thin atmosphere, map its surface, and understand its ancient geology. But their instruments are versatile. And when an opportunity as rare and scientifically priceless as the close pass of 3I Atlas comes along, mission controllers on Earth can repurpose them. On October 3rd, as the comet passes within 30 million kilometers, these Martian orbiters will become our eyes and ears. So, what are they equipped to see? What secrets can they pry from this enigmatic traveler? The Trace Gas Orbiter is the real powerhouse here. It carries two remarkable instruments, Nomad and Axe. Think of them as incredibly sophisticated noses designed to sniff out the faintest trace gases in the Martian atmosphere. They are high-resolution spectrometers, meaning they break down the light they see into its constituent colors, its chemical fingerprint. They can identify specific molecules, water, methane, carbon dioxide, with astonishing precision. Now, imagine pointing those powerful noses not at a planet, but at the glowing coma of a comet. You get the exact same kind of data, a detailed breakdown of the gas composition, a measure of how much of each gas is being produced, and maybe, just maybe, if the signal is strong enough, a reading of the isotopic ratios, the subtle variations in the atoms themselves that act as a birth certificate, telling us about the environment where the object formed. The older Mars Express has its own set of powerful tools. Its SPECOM and Omega instruments are also spectrometers, capable of mapping the distribution of gases and dust in the comet's coma. Omega, in particular, can create spatial maps, showing not just what the coma is made of, but how that material is distributed. It can look for hot spots, for regions where gas and dust production is more intense. It can give us a sense of the comet's three-dimensional structure in a way that a simple point of light never could. What makes this Martian observation window so uniquely valuable is the ability to capture time series data. They won't just take a single snapshot. They will observe the comet repeatedly over several days, watching it as it evolves on its final approach to the sun. Remember that breathing or pulsing behavior that ground-based observers have been reporting? The Mars orbiters might just catch it in the act. They could witness a sudden, episodic outburst, a brilliant spike in carbon dioxide, a burst of water vapor, the sudden appearance of a new chemical species. That kind of observation would be scientific gold. It would be the smoking gun that proves the nucleus is not a uniform snowball, but a complex, patchy, and dynamic world with buried pockets of volatiles, that are just now being exposed to the heat of the sun. It would be the key to testing all those hypotheses about thermal waves and cracking crusts. They can also do something that is very difficult to do from Earth: measure the properties of the dust. As the geometry between the sun, the comet, and the orbiting spacecraft changes over those few days, the way the dust in the coma reflects sunlight will also change. By measuring this change in brightness at different phase angles, scientists can work backward to figure out the size and shape of the dust grains. This might sound like a small detail, but it tells us a huge amount about the nucleus itself. Is it shedding fine, fluffy particles or larger, coarser grains? Is the outgassing a gentle process or a violent one? It's another piece of the puzzle that helps us understand the fundamental nature of this object. But we also need to be realistic about what they can't do. And the biggest thing they can't do is resolve the nucleus. Even from a distance of 30 million kilometers, a nucleus that is at most 5.6 kilometers across will be an infinitesimally small point of light. To the best cameras on these orbiters, it will be utterly indistinguishable from a distant star. They will be able to resolve the structure of the vast, glowing coma around it, perhaps even see the direction of jets. But the solid heart of 3 Atlas will remain hidden, a tantalizing mystery. They also can't watch the comet continuously. These are instruments designed for slow, methodical scans of a planet, not for the rapid-fire observation of a fast-moving target. They have limitations on how quickly they can repoint, on how much data they can store and transmit back to Earth. This isn't a dedicated flyby mission like the ones we've sent to Pluto or Jupiter, with instruments optimized for this specific encounter. This is an opportunistic glance, a bonus piece of science squeezed out of a mission designed for something else. And that brings us to the data itself. The information from Mars doesn't just appear on our screens instantly. The orbiters store their observations on board and then beam them back to Earth during specific communication windows. This means there will be a time lag of hours, or even days, between when an observation is made and when the raw data reaches the scientists on the ground. And that's just the beginning. The raw data then has to go through a complex calibration process. It has to be cleaned of instrumental noise, corrected for the spacecraft's motion, and compared against reference models. This is a meticulous, time-consuming process. So, even if the Trace Gas Orbiter captures something absolutely spectacular on October 3rd, we might not see the fully calibrated, scientifically verified results until mid to late October, or even early November, just as the blackout is in full swing. The European Space Agency has been very clear about this. They will share the results when they are ready. This is the patient, systematic pace of careful science. There are other robotic assets at Mars NASA's MAVEN, Mars Reconnaissance Orbiter, and Odyssey, but their involvement is much less certain. Their instruments are even more specialized for studying Mars, and while they could potentially contribute some data, a position measurement, a reading in the ultraviolet spectrum, no firm observation plans have been announced. They are the wild cards in this Martian encounter. So for these few precious days, Mars is our outpost. It's our forward operating base in the quest to understand this interstellar visitor. The data sent back from these orbiters will not be the dramatic, close-up images that make for a great press release. But they will give us something far more valuable. They will give us the chemistry. They will give us the dynamics. They will provide the crucial ground truth that will allow us to confirm or refute the models we've been building. But they also introduce a new kind of problem. When the Mars observation window closes and Earth's view is still blocked by the sun, we will enter a true blind spot, a period of weeks where we have almost no new information coming in. And it is in that blind spot, that quiet, anxious waiting period, that speculation will thrive. What could happen to 3I Atlas when no one is watching? Why is that period both a scientific headache and a conspiracy theorist's dream? And so, the Martian window closes. Our robotic sentinels have had their brief, precious look. and the data is making its slow journey back to Earth. But now, we enter the most tense and uncertain phase of this entire cosmic drama. From late September through November, as 3I Atlas makes its grand, fiery bow to our sun, our own view from Earth will be stolen from us. This is the great observational blackout, the period of solar conjunction. The term sounds technical, but the reality is beautifully, frustratingly simple. From our perspective, the comet will pass too close to the sun in our sky. Imagine trying to take a photograph of a tiny firefly hovering right next to a brilliant searchlight. The searchlight's overwhelming glare would completely wash out the firefly's delicate glow. That is what will happen to 3I Atlas. The sun's scattered light will saturate our detectors, and pointing a sensitive, multi-billion-dollar telescope too close to the sun is a risk that mission controllers are simply unwilling to take. Even our most powerful space-based observatories, like Hubble and the James Webb Space Telescope, have strict sun avoidance zones they are forbidden from looking into. And so, progressively through October, our view will degrade, until by the time 3I Atlas reaches perihelion on October 30th, we will be almost completely blind. This is a familiar frustration for astronomers. We have seen this play out before, most famously with Comet Eason in 2013. Eason was hyped as the comet of the century, a spectacular sungrazer that was predicted to become as bright as the full moon as it skimmed the sun's surface. The world watched with bated breath. But the most dramatic part of its story, its perihelion pass, happened while it was hidden from our best telescopes. We could only watch with specialized solar observatories, whose low-resolution cameras were designed to watch the sun, not a tiny comet. What they saw was a tragedy. Eason went into the glare as a brilliant comet and emerged on the other side as a faint, dying cloud of dust. It had been torn apart by the sun's immense gravity and heat. The climax of the story, the moment of its disintegration, happened off camera. We only ever saw the aftermath. Now 3I Atlas is not a sungrazer. Its perihelion pass is at a much safer distance, but the principle is the same. The single most interesting moment of its journey, the point of maximum solar heating, when its activity should be at its absolute peak, will occur while our view is almost completely blocked. It is a moment of supreme scientific importance, happening in a near total information vacuum. So, who can still see during this time? Our only eyes will be the solar observatories, spacecraft like SOHO, the Solar and Heliospheric Observatory, and the twin stereo probes. These incredible machines are designed to stare at the sun. SOHO has special instruments called coronagraphs, which use a physical disk to block out the sun's bright face, allowing them to see the faint, ethereal corona, the sun's outer atmosphere. If 3I Atlas passes through this field of view, and if it's bright enough, SOHO will see it as a point of light moving against the backdrop of the solar wind. The stereo spacecraft do the same, but from different angles, giving us a three-dimensional perspective. And this is a huge, but these instruments are not designed for detailed cometary science. They cannot perform spectroscopy to measure the chemical composition. Their resolution is coarse. They can answer a few simple, but crucial, questions. Did the comet survive? Did it brighten or fade dramatically? Did it fragment into multiple pieces? They will give us the broad brush dynamics, the headline of the story, but not the fine print. We will see the comet's behavior in silhouette, a shadow play against the blazing backdrop of the sun, but we won't see the details of its transformation. This is the situation we face. From late October through November, our understanding of 3I Atlas will be based on inference and indirect measurements. We will be trying to reconstruct a story from its echoes. And that leaves room for a lot to happen off camera. Let's game out the possibilities. What could happen to our mysterious visitor while it is cloaked by the sun? One possibility is fragmentation. If that nucleus is indeed a fragile, loosely bound rubble pile, the intense thermal stresses of perihelion could be too much for it. The side facing the sun bakes, while the side facing away remains in deep freeze. This incredible temperature difference could create stresses that crack the nucleus apart. We've seen this happen many times before. If 3I Atlas does disintegrate, we won't know for sure until December, when we can point our telescopes at it again. Instead of a single bright point of light, we would see a faint, diffuse cloud. We'd see multiple, smaller fragments, each on a slightly different path. It would be a disappointing end to the story in some ways, as we would lose our chance to study it over the long term. But even in death, it would give up its secrets. The debris cloud would tell us about the structural strength of interstellar comets and the composition of their interiors. Another possibility is a dramatic change in its rotation. The jets of outgassing gas don't just push the comet. They can also twist it. They can act like torque, spinning the nucleus up or slowing it down. If 3I Atlas has powerful, asymmetric jets that fire off during perihelion while we're not watching, its rotation state could be completely different when we see it again. The pulse or breathing we saw before might have a totally new rhythm, a new period, indicating that the nucleus is tumbling through space in a new way. But the big one, the measurement that every astronomer will be waiting for after the blackout, is the non-gravitational kick. This is the subtle, almost imperceptible change in the comet's path caused by the recoil of its own outgassing. It's the ghost in the machine. As the comet vents its jets of gas, it is pushed, ever so slightly, off the perfect, predictable path dictated by gravity alone. By meticulously comparing its position before perihelion with its position after the blackout, we can measure that push. We can calculate the magnitude and direction of this mysterious non-gravitational acceleration. And this is where the story could take a dramatic turn. If the measured kick is small, and if it perfectly matches the direction and thrust we would expect from the observed outgassing of carbon dioxide, then the case is closed. 3I Atlas is simply a comet. A weird, chemically fascinating, interstellar comet, but a comet nonetheless. Its secrets will be natural ones, telling us about the birth of worlds around another star. But what if the kick doesn't match? What if it's too large? What if it's in a direction that makes no physical sense for a natural jet? What if the object appears to have maneuvered, to have changed its trajectory in a way that cannot be explained by the simple physics of sublimation? That is when the exotic hypotheses, the ones that make the hair on your arm stand up, come roaring back into play. That is the measurement that could change everything. Of course, there is a third, and perhaps most likely, scenario. Nothing dramatic happens at all. The comet could glide through its perihelion pass uneventfully. It could brighten and fade in a smooth, predictable, almost boring way, with no fragmentation, no outbursts, no surprises. It would be the least exciting outcome, and therefore it gets the least amount of attention in the speculative narratives. But in science, a null result, a result that shows nothing unexpected happened, is still a vitally important piece of data. The media dynamics during this blackout period will be a fascinating spectacle in their own. With no new hard data coming in from the major observatories, the narrative space will be left wide open. Speculation will rush in to fill the void. You can expect to see old, pre-blackout images recirculated and reanalyzed, with anomaly hunters picking apart every single pixel. The supposed connection to the Quantico meeting will be rehashed and given new life. Prominent figures like Avi Loeb will likely weigh in with provocative thoughts. By the time we actually reacquire 3I Atlas in early December, the story of what happened during the blackout may have grown and mutated in the telling accumulating, layers of interpretation and conspiracy that may bear little resemblance to the reality. So here is my advice to you as you follow this story. Set your expectations now. The blackout is real. The data gap is unavoidable. Whatever happens to 3I Atlas as it faces the furnace of the sun, we will not know immediately. We will get breadcrumbs from the Mars orbiters. We will get the crude, silhouetted dynamics from the solar observatories. And then we will have to wait. Patience will be our greatest virtue. Early December is when our ground-based assets can finally repoint, when Hubble and the James Webb Space Telescope can once again turn their gaze towards the visitor and start collecting photons. And then, weeks after the main event has already passed, we will finally begin to piece together what truly happened in the dark. If 3I Atlas survives its trial by fire intact, and if its post-perihelion chemistry shows a marked increase in water vapor relative to carbon dioxide, it would be a stunning confirmation of the layered nucleus model. It would mean the sun's heat finally punched through the outer crust and unlocked the water-rich ices buried within. If it fragments, we learn a valuable lesson about the fragile structure of interstellar objects. And if it exhibits that strong, unexplained non-gravitational acceleration, then the door to the most exotic possibilities swings wide open. But here is the beautiful, and sometimes uncomfortable, truth of this endeavor. By the time we have the answers, the most dramatic moment will already be a memory, a ghost on the solar wind. Perihelion happens in the dark, observationally speaking. The universe, in its majestic indifference, does not perform on our schedule. We are cosmic archaeologists, arriving after the event, trying to reconstruct what happened from the echoes and the shadows, from the before and after snapshots, from the models that either fit the data or break under its weight. If 3I Atlas does make it through perihelion, the next chapter of its journey is where we get to test everything we think we know. The outbound leg of its trajectory will take it past Venus, Earth, and Jupiter. These encounters will provide a wealth of new opportunities for coordinated observation, for refining its orbit down to the centimeter, for watching its chemistry evolve in reverse as it cools down and recedes into the deep. That is where the long game of science will be played out. So before we look ahead to that future, we need to step back. We need to look not just at the comet, but at the story we are telling about it. Because 3I Atlas has become more than just an object. It has become a narrative, a mirror reflecting our own hopes, fears, and the very way we make sense of the unknown. Let's take a step back from the science for a moment, from the spectral lines, the orbital mechanics, the chemical ratios, and talk about the story. Because 3I Atlas is no longer just an astronomical object. It has transcended that. It has become a narrative, a canvas onto which different groups are painting vastly different pictures. And if we want to truly understand this moment, we have to understand the stories being told, because these narratives are shaping what we believe, how we feel, and how we will ultimately respond to whatever comes next. On one side of this narrative divide, you have the institutions, the National Aeronautics and Space Administration, the European Space Agency, the professional astronomical community. Their story is the one we've been piecing together from the facts. It is a story told in a measured, cautious, and deeply technical language. It's a story found in blog posts about Hubble observations, in dense preprint papers detailing spectroscopic results, and in frequently asked questions pages that explain the dry but essential physics of orbital mechanics. Their press releases often read like technical documentation, because in many ways, that's precisely what they are. This is the traditional form of science communication, authoritative, meticulously vetted, and, by the standards of the modern world, incredibly slow. On the complete opposite side, you have the alternative narratives. These are the stories that flourish in the fertile ground of social media, on YouTube channels with ominous music, and in sprawling Reddit threads. This is the story that asks, what is NASA hiding? It's the story that boldly declares the Comet A probe and connects the dots between 3I Atlas, the Quantico meeting, decades-old UAP reports, and grand conspiracy theories about the suppression of alien contact. These narratives are the polar opposite of the institutional ones. They are fast, emotionally resonant, and built for maximum shareability. They don't wait for the slow process of peer review. They don't hedge their bets with uncertainties or error bars. They tell a clean, compelling story with clear heroes, the truth seekers and villains, the secretive institutions. And then, caught in the crossfire between these two extremes, you have the vital middle ground. This is where you find the scientists, like Avi Loeb, who are willing to publicly entertain the exotic hypotheses, pushing the boundaries of the mainstream conversation. It's where you find the skilled amateur astronomers, sharing their raw, unvarnished observations. It's where you find the best science communicators, trying to do the difficult work of explaining the actual, complex data while still acknowledging the genuine, tantalizing weirdness of it all. This middle ground is where most of the interesting, productive conversation is happening. But it's also the hardest space to occupy. You are constantly being pulled towards the rigid caution of the institutions on one side, and the sensational, viral pull of the alternative narratives on the other. The fundamental problem lies in the asymmetry of our modern media ecosystem. Caution simply doesn't go viral. A headline that reads, NASA observes interstellar comet with unusual but plausibly natural chemical signature, might get a few hundred clicks from interested science fans. A headline that screams, alien probe approaching Mars while NASA stays silent, can get hundreds of thousands, or even millions, of clicks. The very incentive structure of digital media, the algorithms that decide what you see, rewards novelty, certainty, and high emotional impact. A calm, measured, nuanced analysis simply doesn't deliver on any of those metrics. So, what happens? The sensational claims spread exponentially faster and farther than the sober corrections. By the time a professional astronomer takes the time to publish a detailed blog post explaining, with diagrams and models, why the sunward tail is just a well-understood anti-tail illusion, the original viral post claiming it's a sign of propulsion has already been shared 10,000 times. You can't unring that bell. The careful correction will only ever reach a tiny fraction of the audience that saw the initial exciting claim. This isn't a new phenomenon, but the speed of social media has accelerated it to the point where the narrative can become self-sustaining. It begins to feed on itself, accumulating new layers of inference and evidence that become harder and harder to disentangle from the truth the longer they persist. The Quantico meeting is the perfect case study in how a simple coincidence becomes proof in the absence of official information. As we've established, there is no public link between that meeting and 3I Atlas, but the timing creates a powerful association. The human brain is, above all else, a pattern-matching machine. It is one of our greatest strengths and our most dangerous weaknesses. We see two dramatic events happening at the same time, and our brains instinctively infer a causal link. Secret military meeting happens. Mysterious comet arrives. Therefore, the meeting must be about the comet. That isn't a logical deduction. It is a narrative construction. But it feels logical because the pattern is so clean and compelling. Once that association is made, every piece of ambiguity becomes fuel for the fire. Why won't the military say what the meeting was really about? They must be covering up the space connection. Why is NASA being so quiet about 3I Atlas? They must be coordinating their story with the military. Every absence of information is twisted into positive evidence for the narrative. The responsible framing, which is to acknowledge both events while making no claims of a connection, is much harder to maintain. It requires intellectual discipline. It requires you to be comfortable living with uncertainty. And most people don't want uncertainty. They want answers, and they often prefer a simple, dramatic answer, even if it's wrong, over a complex and unresolved truth. This story is resonating so deeply because we've been primed for it. The fierce debates around Oumuamua created a template in the public consciousness. Its strange shape, its unexplained acceleration, and Avi Loeb's bold alien light sail hypothesis laid the groundwork. Now, When a new interstellar object arrives, people instinctively try to map that old template onto it. They look for the same story beats. Does it have an unusual shape? We don't actually know. Is it showing anomalous acceleration? We haven't measured that yet. Are the institutions being silent? They're not actually silent, just not sensational. It's that pattern-matching instinct at work again, trying to make the new and unknown fit into a familiar story, even when the facts are fundamentally different. This is the central tension of the story of 3I Atlas. The institutions, with their long memory of past mistakes, are incentivized to avoid overstatement. Their credibility is their currency. But their caution, in this supercharged environment, looks like suppression. The content creators, meanwhile, are rewarded by the algorithms for novelty and boldness. A video titled "The 3I Atlas Mystery Deepens" will always perform better than one titled "The Chemistry of 3I Atlas" is somewhat unusual. The algorithm doesn't care about scientific accuracy. It cares about engagement. And engagement correlates with emotional intensity, not with intellectual humility. The institutions are playing a long, slow game of chess, while the internet is playing a fast, chaotic game of poker. And the public is caught in the middle, trying to figure out who to trust. To navigate this story responsibly, we have to become aware of the cognitive traps that are laid out for us at every turn. These aren't malicious tricks. They are simply the quirks of the human mind, the shortcuts our brains take to make sense of a complex world. And in a story as ambiguous and emotionally charged as this one, these traps are everywhere. Naming them is the first step to avoiding them. First, there's cherry picking. This is the act of selecting only the pieces of evidence that fit the narrative you want to believe, while conveniently ignoring the pieces that don't. If you are determined to believe that 3I Atlas is an artificial object, you will focus intensely on the strange sunward tail, the mission-like trajectory, and the timing of the Quantico meeting. You will tend to downplay or ignore the spectroscopy that shows it as made of perfectly normal cometary volatiles, the complete lack of any radio signals, and the fact that its brightness variations are consistent with a natural rotating body. It's about building a case, not seeking the truth. Next is the powerful argument from ignorance. This is the logical fallacy of assuming that if something has not been proven false, it must therefore be true. You will hear this a lot. Well, NASA hasn't definitively ruled out that it's an artificial probe, have they? This is a complete inversion of the scientific method. The default assumption, a null hypothesis, is always that an object is natural. The burden of proof lies on the person making the extraordinary claim. An absence of disproof is not, and never will be, proof. Then we have the conjunction fallacy, a subtle but powerful trap. This is our brain's tendency to believe that a specific, detailed story is more likely to be true than a general simple one. Consider these two statements. Statement A: 3I Atlas is a comet with an unusual chemical composition. Statement B: 3I Atlas is an alien reconnaissance probe sent by an ancient civilization to study multiple planets in our solar system on a pre-programmed trajectory. For many people, Statement B feels more compelling, more plausible, because it has a rich narrative structure. It tells a story. But in terms of probability, the far simpler, more general explanation is almost always the more likely one. A narratively satisfying story is not necessarily a factually likely one. And finally, there is the mother of all cognitive traps, confirmation bias. This is our deep-seated tendency to interpret new, ambiguous evidence as confirmation of what we already believe. The institutional silence is the perfect Rorschach test for this. If you already believe that our institutions are secretive and prone to cover-ups, then their cautious, bureaucratic communication style is slam-dunk evidence that they are hiding something. If you already believe that these institutions are generally trustworthy and scientifically rigorous, then you will see that exact same communication style as appropriate, responsible caution. The evidence is the same. The interpretation is shaped entirely by our pre-existing beliefs. So, how do we cut through this cognitive fog? How do we stay open-minded to the genuine anomalies and the possibility of a profound discovery, without falling for every sensational claim that comes along? We need to equip ourselves with a toolkit for productive skepticism. First, demand provenance. When someone shares a dramatic image or makes a bold claim, your first question should always be, where did this come from? What instrument captured it? What is the exact timestamp? What was the viewing geometry? If those crucial details are not provided, you should be immediately suspicious. A picture without context is not data. It's just a pretty picture. Second, prefer trends over snapshots. A single spectacular image could be anything: an instrumental artifact, a processing error, a lucky cosmic ray hit. But if that same strange feature appears consistently across multiple observations from different instruments at different times, then it is far more likely to be real. A single frame is an anecdote. A long-term light curve is data. Third, look for independent confirmation. If 3I Atlas is truly doing something anomalous, more than one observatory should see it. Do the spectroscopy results from the James Webb Space Telescope match the results from the big ground-based telescopes? Do the astrometric measurements from professional observatories line up with the best data from the amateur networks? This process of cross-validation is the immune system of science. It's how the community filters out mistakes and artifacts. Fourth, follow the experts, but don't worship them. A figure like Avi Loeb is a credentialed, brilliant Harvard astronomer. His hypotheses are absolutely worth considering and taking seriously. But it's also important to know that he is an outlier in his field. His most exotic ideas are not the mainstream consensus. We need to be able to tell the difference between a bold, contrarian hypothesis and established consensus science. Both have value, but they are not the same thing. And finally, and perhaps most importantly, look for falsifiable predictions. The statement, 3I Atlas might be artificial, is not a scientific hypothesis. It's too vague. It's not falsifiable. You can always just claim the evidence is still hidden. But the statement, if 3I Atlas is an artificial probe, then it should exhibit non-gravitational accelerations that are inconsistent with its observed outgassing, or it should be emitting structured radio signals. That is a beautifully scientific and falsifiable prediction. We can test that. We can point our radio telescopes at it. We can precisely measure its trajectory. If those predictions fail, if we find no radio signals, and if its accelerations perfectly match the outgassing models, then the hypothesis is weakened or even ruled out. That is how science progresses. This is the challenging but essential work we must do as engaged observers of this story. We must learn to separate the signal from the noise. We must be willing to live with uncertainty and to update our beliefs as new data comes in. And we must remember that even the boring explanation that this is simply the weirdest natural comet we have ever discovered is still a mind-blowing and wonderful outcome. It would still tell us incredible new things about the diversity of worlds forming around other stars. You don't need to invoke aliens to make this story interesting. The universe, in its boundless creativity, is already strange enough on its own. Now, with this framework in place, let's build our own hypothesis bank. Let's lay out the full spectrum of possibilities, from the most mundane to the most extraordinary, and define exactly what evidence we would need to see in the coming months to support or refute each one. Let's turn our speculation into a testable scientific decision tree. All right, let's do something that is at the very heart of the scientific process. Let's build a library of possibilities. Science doesn't work by proving a hypothesis is true. It works by proposing multiple explanations and then systematically trying to break them. The hypothesis that survives this rigorous, often brutal process of elimination is the one we are left with. It's a bit like a cosmic detective story. You line up all the suspects, from the most likely to the most outlandish, and you look for the evidence that will rule them out, one by one. So, let's line up our suspects for the identity of 3 I-Atlas. Suspect number 1, the alien chemist, our baseline hypothesis. This is our starting point, a most conservative and scientifically grounded explanation. It posits that 3 I-Atlas is a completely natural comet, but one that was born in an interstellar environment where the chemistry was fundamentally different from our own. Perhaps its parent star had a much higher ratio of carbon to oxygen than our Sun. Or perhaps the comet formed in the frigid outer reaches of a protoplanetary disk, a region so cold that carbon dioxide ice was far more common and stable than water ice. In this scenario, the bizarre 8-to-1 carbon dioxide to water ratio isn't a sign of anything exotic or technological. It's a genuine chemical fingerprint of its alien birthplace. It's a messenger telling us, this is how worlds are built somewhere else. What would the evidence look like? The predictions are straightforward. As we continue to observe it, especially after perihelion, strong carbon dioxide emissions will persist as its dominant feature. We might see the water signal increase a little bit as the sun's heat penetrates deeper, but it will never come close to dominating. Any non-gravitational accelerations we measure will be perfectly consistent in both magnitude and direction with the chaotic, messy outgassing of these CO2 jets. How could we rule it out? If, after perihelion, water vapor suddenly becomes the dominant gas, that would be a problem for this simple model. If we measure non-gravitational accelerations that are far too large for the amount of gas we see being produced, this hypothesis breaks. Suspect number 2, the cosmic gobstopper, the layered nucleus hypothesis. This is a more nuanced, but still entirely natural explanation. It suggests that the nucleus of 3 I-Atlas isn't chemically uniform, but is instead layered, like a gobstopper. The outer shell is a crust of carbon dioxide-rich ice and dust, which has acted as an insulator for millions of years. But buried deeper within this crust is a core of familiar, water-rich ice. As the comet approaches our Sun, a slow-moving thermal wave of heat begins to propagate inward. The CO2 on the surface is the first to sublimate, which is what we are seeing now. But the water is still waiting its turn, locked in the frozen depths. What would the evidence look like? This hypothesis makes a very specific, testable prediction about timing. We should see a dramatic evolution in the comet's chemistry. Before and during perihelion, it will be CO2 dominant. But after perihelion, as that thermal wave finally reaches the deeper layers, we should see a significant increase in water vapor. The CO2 to water ratio should drop from 8-to-1 down towards something more typical, maybe 2-to-1 or even 1-to-1. The observations in December and beyond will be the key test. How could we rule it out? If the chemistry stays static, if months after its closest approach to the Sun, 3 I-Atlas is still overwhelmingly dominated by carbon dioxide, then the thermal wave should have had plenty of time to unlock any buried water. A lack of chemical evolution would be strong evidence against this layered model. Suspect number 3, the smoke and mirrors comet, the dust and geometry hypothesis. This hypothesis focuses on explaining the visual weirdness, the sunward plumes, the strange tail structures, without resorting to exotic physics. It proposes that the nucleus is shedding unusually large dust grains, perhaps millimeter or even centimeter sized. These larger grains are not easily pushed around by the gentle pressure of sunlight. Instead of streaming away to form a classic tail, they tend to follow the comet's own orbital path more closely, spreading out along its trajectory like a trail of cosmic breadcrumbs. From our specific viewing angle on Earth, this trail of dust can create powerful optical illusions, making it appear as if there is a spike or a tail pointing towards the Sun. It's all a trick of geometry and perspective. What would the evidence look like? The key prediction is that these strange features should change, or even disappear, as our viewing angle changes. As the Earth, the Sun, and the comet all move, our geometric perspective will shift. The features should evolve in a predictable way that can be precisely modeled. Spectroscopy of these features should also show only the reflected light of dust, with no evidence of gas emissions. How could we rule it out? If the sunward feature persists regardless of our viewing geometry, if its shape changes in ways that are inconsistent with the simple ballistic motion of dust, or most damningly, if our spectrometers detect the chemical fingerprint of gas in this anti-tail, then it's not just an illusion. It's something real, and it needs a different explanation. Suspect number 4, the volcanic snowball, the cryovolcanic pockets hypothesis. Now we start to push into less common, but still plausible territory. What if the nucleus isn't just layered or patchy, but is structurally complex, riddled with subsurface cavities or fractures filled with highly pressurized, exotic ices? As the surface heats up and sublimates away, it could suddenly expose one of these pockets. The result would be a cryovolcanic eruption, a sudden, violent outburst of gas that could have a completely different chemical composition from the surface ice. This could be where we see trace species that hint at even stranger chemistry: sulfur compounds, nitrogen compounds, complex hydrocarbons. What would the evidence look like? We would expect to see sporadic, sudden outbursts in the comet's brightness that are correlated with the rotation of the nucleus as new areas are exposed to sunlight. Our time series spectroscopy from the Mars orbiters or from the post-blackout observations would be crucial here. We would be looking for transient features, chemical emission lines that appear for a few hours or a few days and then vanish just as quickly. How could we rule it out? If the comet's activity is smooth and predictable, if there are no sudden outbursts, and if the chemistry remains boringly consistent over time, then we don't need to invoke a complex internal plumbing system. A simple sublimating surface would explain everything. This library gives us a framework. It turns our vague questions into a concrete set of testable predictions. The data that we are collecting right now from Mars, and the flood of data that will come in December, will allow us to walk through this library and start taking books off the shelf. Each piece of new evidence will act as a filter, eliminating possibilities and bringing us closer to the truth. And it is the evidence from the Mars flyby, the event that is happening as we speak, that will provide our very first crucial filter. Let's zoom in on that encounter and define what, exactly, we should be watching for. Right now, at this very moment, as you are listening to this, the first chapter of the climax of this story is being written. 3I Atlas is making its closest approach to the planet Mars, and the European Space Agency's robotic orbiters, our silent proxies in the deep, are conducting their observation campaign. This is not a future event to be anticipated. It is the present reality. The photons of light carrying the secrets of this interstellar traveler are, at this instant, striking the detectors of our instruments. So, what should we be watching for? As the data from this encounter begins to trickle back to Earth over the coming days and weeks, what specific measurements will be meaningful? What would constitute a genuine surprise, and what would bring a reassuring sense of normalcy? First and foremost, this is a chemistry story. The most important clues will be written in the language of molecules. The James Webb Space Telescope gave us a single stunning snapshot back in August. A world dominated by carbon dioxide. But that was just one moment in time, when the comet was farther from the sun and less active. Now, as it heats up on its final approach to perihelion, the central question is, does that chemistry shift? If that layered nucleus hypothesis is correct, this is where we might start to see the first hints of it. We would be looking for the signature of water vapor beginning to emerge from beneath the CO2-rich crust. The ratio might start to drop from that shocking 8-to-1 down towards a 5-to-1, or even a 3-to-1, even a small, but statistically significant, increase in the water signal would be a huge discovery. It would tell us that water is indeed present, just buried, and that the comet's character is evolving as it warms up. Alternatively, if the carbon dioxide signal remains absolutely dominant, if that 8-to-1 ratio holds steady or even increases, it would be powerful evidence for the simpler alien chemist hypothesis. It would suggest there are no hidden layers, that this is just a comet that is fundamentally, through and through, a creature of carbon dioxide. But the devil is in the details, in the trace species. Remember that carbonyl sulfide that Webb detected? Does its abundance change? More excitingly, do completely new molecules appear in the spectra? The sudden appearance of sulfur dioxide, or ammonia, or methane would be like finding a new word in the comet's chemical dictionary. These molecules tell us about the specific conditions, the temperature, the pressure, the radiation environment of the protoplanetary disk where this object was born. And if we were to detect any complex organic molecules, even simple ones like formaldehyde or methanol, the astrobiology community would be ecstatic. Not because it would mean life, but because these are the fundamental building blocks of life as we know it. Finding them in a visitor from another star would suggest that the raw ingredients for life are not unique to our own solar system, but are being seeded throughout the galaxy. The holy grail of this encounter would be to measure the isotopic ratios. This is incredibly difficult to do, but the instruments on the trace gas orbiter might just be sensitive enough. Isotopes are slightly heavier or lighter versions of the same chemical element. For example, heavy water contains a version of hydrogen called deuterium. The ratio of deuterium to normal hydrogen in a Comet S water is a direct fingerprint of the temperature at which that water ice formed. If we could measure that ratio in 3I Atlas, it would be like getting a direct temperature reading from its alien birthplace. It would be a discovery worthy of the front page of the world's most prestigious scientific journals. Next, we look at the morphology, the shape and structure of the dust. As the Mars orbiters view the comet from different angles over their week-long observation window, we can test that smoke and mirrors hypothesis about the anti-tail. If those strange sunward plumes are purely a trick of geometry, their appearance should change in a predictable way as the orbiter's viewing angle shifts. If a feature that looks like a sunward spike from one angle looks more like a conventional, curved tail from another, then we can confidently say it's an illusion. But if that sunward feature persists, regardless of the viewing geometry, then it becomes much harder to explain. It would suggest that something is actively ejecting material in a non-ballistic way. The Omega instrument on Mars Express, with its ability to create spatial maps of the coma, might even be able to resolve localized jets, bright spots of concentrated gas and dust production. This would be visual confirmation that the nucleus has specific active regions, providing strong support for the patchy surface model. And then there's the subtle, but perhaps most profound measurement of all, the non-gravitational probe. The astrometric data, the precise position measurements taken by the Mars orbiters before, during, and after the flyby will allow scientists to fit the comet's orbit with unprecedented precision. Any tiny deviation from a purely gravitational path will show up, and the key question will be, do these deviations make sense? If you see a strong jet of carbon dioxide in the spectral data, you can calculate exactly how much of a push it should give the comet. The math is simple. It's the basic rocket equation. Does the measured acceleration match the predicted acceleration from the observed gas? If the answer is yes, then everything is consistent with a natural outgassing comet. If the answer is no, if the push is too big or in the wrong direction, then we have a genuine mystery on our hands. The Mars encounter is so valuable here because it provides a long baseline of observation over a very short period of time, which can reveal these subtle accelerations much more clearly than the more sporadic observations from Earth. We also have to remember the immense value of a null outcome. If the Mars observations come back and show nothing, If the chemistry is perfectly consistent with what the James Webb Space Telescope saw, if the dust behavior is completely normal, if there are no surprises, no anomalies, that in itself is a hugely valuable scientific result. A boring result powerfully narrows the hypothesis space. It tells us that, at least during this phase of its journey, 3I Atlas is behaving exactly like a comet should, just one with a very strange initial ingredient list. Science isn't just about finding the weirdness. It's about establishing the baseline of what is normal. And finally, we have to state this clearly once again. Don't expect these results to appear overnight. The calibration pipelines for this kind of data are complex. The internal review process within the science teams is rigorous. The coordination between the international agencies is deliberate. Realistically, we might not see the first fully calibrated, peer-reviewed data from this Mars encounter until late October or early November, right when we're entering the solar blackout. We have to be patient. We have to understand that in the world of careful science, delay does not equal suppression. Delay is the price of rigor. If you want fast, you get sloppy. If you want the truth, you wait. And as that precious Martian data makes its long journey home, the comet itself continues its own inexorable journey towards the sun. The Mars window will close. The Earth-based assets will lose their view. And then we will face the moment of peak drama, the crucible of perihelion itself, where 3I Atlas will either survive, disintegrate, or be transformed into something else entirely. The date is October 30th, 2025. This is the moment the entire story has been building towards. Perihelion. It is the point of closest approach to the sun, a fiery crucible where the fate of 3I Atlas will be decided. It will pass at a distance of approximately 1.4 astronomical units, or about 210 million kilometers. Now, this is not a death-defying plunge into the sun's corona. It's a safe distance, well inside the orbit of Mars, but comfortably outside the orbit of Earth. But for a visitor that has spent millions, perhaps even billions, of years in the profound, abyssal cold of interstellar space, this is the hottest it has been since the day it was born. For a comet, perihelion is the ultimate moment of truth. Imagine all the stresses that have been building within this tiny, frozen world. All the volatile ices, buried deep in its interior, have been slowly warming, creeping towards their sublimation points, turning from solid to gas. The incredible temperature differential between the sun-baked side and the frozen night side is creating immense thermal shocks, threatening to crack its very structure. Everything is coming to a head, and we will see almost none of it. We will be on the other side of the stage, shrouded in the sun's glare, forced to infer what happened in the heart of the fire from the evidence that emerges from the smoke. So, let's become cosmic odds makers. Let's game out the scenarios. What could happen to our traveler as it faces its trial by fire? What would each outcome look like, and how would we know the difference? Scenario A, the ghost of ISON disintegration. Every astronomer who predicts the fate of a comet is haunted by the ghost of Comet Isen. That was the sun grazer that was supposed to put on a spectacular show, but instead it met a tragic end, torn apart by the sun's forces. Could 3I Atlas suffer the same fate? While the tidal forces at its perihelion distance are negligible, the thermal stress is very, very real. If the nucleus is indeed a loosely bound rubble pile, if the icy matrix that acts as the glue holding it all together finally sublimates away, the entire structure could simply crumble and fall apart. How would we know? The signatures of this kind of disruption would be unmistakable once we reacquire the target in December. Instead of a sharp, compact coma with a bright central point, our telescopes would see a faint, diffuse, and elongated cloud. The overall brightness would be far, far lower than predicted. Trying to plot its orbit would become a nightmare. Instead of tracking a single, coherent object, astronomers would be trying to fit an orbit to a messy, expanding debris field. The spectra of this cloud might also show an unusual ratio of dust to gas, with far more dust than expected, the pulverized remains of the nucleus. If this happens, it would be a bittersweet outcome. We would lose our chance for a long-term study of this incredible object, but in its death, it would reveal its innermost secrets about its structure and composition. Scenario B, the survivor, graceful survival. Contrast the fate of Isan with another famous sun-grazer, Comet Lovejoy. Lovejoy plunged deep into the sun's corona, a region where temperatures reach millions of degrees, and somehow, miraculously, emerged on the other side, battered and outgassing furiously, but with its nucleus structurally intact. 3I Atlas is facing a far less harsh environment, so a graceful survival should be our default expectation. How would we know? This is the boring outcome, but boring is often correct. A graceful survival would mean a smooth, predictable light curve through the perihelion period. When we see it again in December, it would look healthy, a bright, compact coma with a clear central condensation. Its chemistry would have evolved, as expected, but nothing catastrophic would have occurred. The non-gravitational accelerations would be perfectly consistent with its outgassing. No fragmentation, no sudden, dramatic changes. While this might be the least exciting scenario from a narrative perspective, from a scientific one, it's a huge win. It would mean we get months, or even years, of additional observations as it journeys back out of our solar system. We could track its cooling process, watch to see if water finally does dominate over the carbon dioxide, and study how its jets evolve over the long term. This story would continue. Scenario C, the Phoenix, a dramatic flare. Some comets don't just survive perihelion, they put on a show. There is a phenomenon known as an outburst, a sudden, explosive release of volatiles that can cause a comet to brighten dramatically, sometimes by a factor of 1,000,000, in just a matter of hours. The famous comet Holmes did this in 2007, flaring up so brightly that it became a naked-eye object for a time. Nobody saw it coming. The cause is thought to be either the sudden exposure of a massive subsurface pocket of highly pressurized gas or a structural collapse, like a cosmic landslide that exposes a huge area of fresh volatile ice to the sun all at once. How would we know? If 3I Atlas has a major outburst at perihelion, our very first sign would likely come from the solar observatories, SOHO or Stereo, which would register a sudden, dramatic surge in its brightness. Then, when we reacquire it in December, it would be stunningly brighter than all the models predicted. Its coma would be vast and incredibly active. Its spectra might even show new trace species, the chemical signatures of the deeper material that was violently excavated during the eruption. An outburst would be scientifically thrilling, but it would also be narratively explosive. It would instantly pour gasoline on the fire of the alien tech speculation, because a sudden, dramatic change in brightness can look, to a mind primed for patterns, like a deliberate act. But we must remember, outbursts are a known, if poorly understood, natural cometary behavior. The key to distinguishing a natural outburst from something truly exotic would be to check the energetics. Is the amount of energy released consistent with the sublimation of ice? If yes, it's a natural, albeit spectacular, outburst. If no, if there's more energy being released than can be explained by chemistry, then we would have a very good problem indeed. The thermal physics at play here are immense. At 1.4 astronomical units, the sun's energy flux is about 500 watts per square meter. That's still enough to boil water many times over. For an object that has been in a deep freeze for eons, this is an incredible shock to the system. And that heat doesn't penetrate instantly. Ice is a terrible conductor of heat. This means the surface of the nucleus can be baking, while just a few meters inside, the ancient ices remain frozen solid. This creates a steep temperature gradient and a built-in time lag. This is why we might not see the peak of activity like the release of water vapor, until after the peak of solar heating. There's a hysteresis, a delay, built into the system. So, these are the scenarios we face at perihelion, the testable predictions for each: disruption, survival, or a dramatic outburst. And we must accept the communication reality now. We will not know which of these scenarios has unfolded until weeks after it has already happened. Soho and stereo will give us the early hints, but the full picture awaits our view in December. This is the profound frustration and the deep fascination of astronomy. The universe does not perform for our convenience. The most important moments often happen while we are blind. We are left to reconstruct the truth from the echoes and the shadows. And it is a big if 3i, Atlas makes it through this trial by fire, then the outbound leg of its journey is where the real long-term science of understanding this messenger from another world will truly begin. Let us assume for a moment the most optimistic and scientifically fruitful outcome: survival. Let us imagine that 3i Atlas endures its fiery perihelion pass, that it emerges from the sun's glare in December, not as a fading ghost or a shattered wreck, but as a healthy, active, and profoundly interesting comet. If that happens, then the story is far from over. In fact, the most important chapter is just beginning. The outbound leg of its journey, its long goodbye to our solar system, is where we will have the chance to move beyond the snapshots and the speculation and into the realm of deep, long-term characterization. This is where we will truly get to know our visitor. After swinging around the sun, the comet's trajectory will carry it on the next phase of its grand tour. It will cross the orbits of Venus and Earth, and then head out towards the realm of the giants, passing Jupiter in the spring of 2026. This long, leisurely departure provides a golden opportunity for a sustained, coordinated observation campaign. This will be our chance to watch, in reverse, the processes that brought the comet to life. We will get to see how its chemistry and behavior evolve as it cools down, as the intense solar heating wanes, and as it begins its long journey back into the interstellar deep freeze. The single most important question we will be trying to answer during this phase is the fate of the water. Will the post-perihelion observations finally reveal the strong signature of H2O that has been so conspicuously absent? If the layered nucleus or thermal lag models are correct, this is exactly what we should expect to see. The heat from perihelion, having finally had weeks to penetrate into the deeper layers of the nucleus, should have unlocked the vast reservoirs of buried water ice. The post-blackout spectra should show the water vapor signals strengthening day by day, perhaps even eventually surpassing the carbon dioxide. Seeing this chemical transformation happen in real time would be a stunning piece of observational science. It would be a powerful confirmation that the comet's interior is indeed different from its surface. But what if it doesn't happen? What if, even weeks and months after perihelion, carbon dioxide remains the undisputed king of the coma? That would be an equally profound, though perhaps more puzzling, result. It would strongly suggest that the simple alien chemist hypothesis is correct, that this is an object that is just fundamentally, and perhaps uniformly, CO2 rich. It would force us to confront the reality that the building blocks of comets in other solar systems can be radically different from our own. The long outbound arc of its trajectory will also be the definitive test for any non-gravitational accelerations. With every new observation we take in December, in January, in February, the precision of its orbit will get better and better. We will be able to track its path with almost unbelievable accuracy. Any tiny, persistent push from outgassing jets will accumulate over time, becoming more and more obvious in the data. This is where we will finally be able to answer the question of intent versus nature. We will be able to calculate the total kick it received during its perihelion pass and compare it to the total amount of gas we saw it emit. If the numbers line up, the natural comet hypothesis will be placed on an incredibly firm footing. But if they don't, if there is a persistent, unexplained acceleration that cannot be accounted for by the physics of sublimation, then the debate about the true nature of 3I Atlas will ignite in a way we can scarcely imagine. This is also our chance to get a much better handle on its physical properties. The long-term light curve, the detailed record of its brightness variations over many months, will allow us to nail down its rotation period with extreme precision. We might even be able to model the shape of the nucleus and the location of the active regions on its surface that are producing the jets. We will watch how those jets evolve as the comet cools. Do they sputter out one by one? Do they change their intensity? Do they settle into a steady, predictable pattern, or do they remain chaotic and flickering? Each of these behaviors tells us something new about the structure and composition of this alien world. And as 3I Atlas heads out towards Jupiter, we may get a final tantalizing bonus. The European Space Agency's JUICE, Jupiter Icy Moons Explorer, mission is already on its way to the Jovian system. While its instruments are designed to study Jupiter and its moons, it's possible that mission controllers could use them to take a final, distant look at our interstellar visitor as it passes by. The data would be faint and difficult to obtain, but it would provide another invaluable data point, another piece of the puzzle in this extraordinary scientific detective story. But the long goodbye is about more than just data. It's about the culmination of the narrative. As the hard evidence accumulates, as the uncertainties shrink, and as the scientific consensus begins to form, the wild speculation will slowly give way to a more sober understanding. The story will transition from a mystery fueled by an absence of information to a history written in the hard currency of data. We will move from asking, "What if?" to stating what is, and what is at stake in this final chapter. Nothing less than our place in the cosmos. If 3I Atlas turns out to be a completely natural, albeit chemically unusual, comet, it will still be a revolutionary discovery. It will provide us with our first detailed glimpse into the chemistry of planet formation around another star. It will show us that the processes that built our own solar system are not the only way to build one. It will be a testament to the incredible diversity of the galaxy. It will be a beautiful, inspiring story of the power of science to reach out across the interstellar void and touch the unknown. But if it turns out to be something else, if the data that comes in during this long goodbye stubbornly refuses to fit our natural models, if the anomalies not only persist, but grow stronger and more inexplicable, then we will find ourselves standing on the precipice of a discovery that would reshape human history. The stakes are that high. So, as we wait for the perihelion blackout to end, as we anticipate that first trickle of new data in December, we must prepare ourselves for all possibilities. We must hold our hypotheses lightly, be ready to abandon our pet theories in the face of new evidence, and follow the data wherever it leads, even if it leads us to a place that is uncomfortable, challenging, and profoundly strange. The long goodbye of 3I Atlas will be a final extended lesson in the art of listening to the universe. And the universe is about to speak. The only question is, will we be ready to hear what it has to say? As we stand at this incredible juncture, caught between the tense anticipation of the blackout and the promise of discovery on the other side, it's worth taking a final step back. Let's look past the immediate questions of chemistry and trajectories and ask a deeper one. What does this event, the passage of 3I Atlas, truly mean? What is the larger story that is unfolding here? Because this isn't just about a single strange comet. It is about a moment of profound reflection. In this mysterious visitor from another star, we are seeing a mirror held up to ourselves, to our science, to our societies, and to our deepest, most fundamental assumptions about our place in the universe. For decades, our search for cosmic companionship has been largely a passive one. We have been listeners. With our radio telescopes pressed to the ear of the cosmos, we've been waiting for a faint, intelligent whisper from the stars, a sign that we are not alone. It has been a patient, often lonely, vigil. But the arrival of Oumuamua, and now 3I Atlas, has fundamentally changed the nature of that search. The universe, it seems, is not just waiting for us to listen. It is actively sending messengers to our doorstep. We are no longer just listeners. We are becoming greeters, analysts, and interpreters of physical artifacts that have made the journey from there to here. This is a monumental shift. It means that the study of extraterrestrial intelligence, and indeed extraterrestrial life, is moving from the realm of pure speculation into the realm of observational, testable, physical science. We can now touch, taste, and analyze the chemistry of other solar systems. That alone is a revolution. The story of 3I Atlas is also a powerful, and at times uncomfortable, reflection of the age we live in. The stark contrast between the slow, cautious, and fragmented communication from our scientific institutions and the rapid-fire, sensational, and often baseless speculation that explodes across social media is not a story about a comet. It's a story about our modern information ecosystem. It's a story about the erosion of trust in institutions and the seductive power of narratives that confirm our biases. We are watching a real-time case study in how a complex, uncertain scientific reality is processed, distorted, and amplified through the prism of our hyper-connected world. Navigating this new landscape, where the signal of genuine discovery can be so easily drowned out by the noise of misinformation, is one of the single greatest challenges of our time. Getting the story of 3I Atlas right isn't just about good science. It's about practicing good intellectual citizenship. This event also holds up a mirror to the very nature of science itself. We often talk about science as a machine that produces facts, a dispenser of certainty. But the story of 3I Atlas reminds us that science, in its truest form, is not about having all the answers. It is about the profound and often humbling process of asking the right questions. It is about living with uncertainty, sometimes for a very long time. It's about building models and then, with a kind of joyful ferocity, trying to break them with new data. The messy, confusing, and contradictory process we are witnessing, the debates, the competing hypotheses, the frustrating gaps in our knowledge, that is not a sign that the scientific process is failing. That is the scientific process in action. It's a reminder that discovery is not a single eureka moment, but a long, slow, and arduous journey out of the fog. And what if, after all of this, the final answer is a simple one? What if 3I Atlas is just a weird comet? There will be those who feel a sense of disappointment, a letdown. The grand cinematic story of an alien probe will have dissolved into a more mundane academic reality. But to feel that way would be to miss the deeper magic of what has happened. To be able to say, with certainty, this piece of the universe was born in a place where carbon dioxide, not water, is the dominant ice, is a piece of knowledge that our ancestors could have scarcely dreamed of. It would be a concrete physical clue that helps us understand the vast, creative diversity of the cosmos. It would tell us that our own solar system, which we once thought was the template for all others, is just one possible outcome of the great cosmic experiment. The universe doesn't need to send us spaceships to be awe-inspiring. A simple, chemically strange snowball, a messenger from a star we will never know, is more than enough to fill us with wonder. Ultimately, the story of 3I Atlas is a reflection of our own evolving cosmic perspective. For millennia, we have looked up at the stars and seen them as distant, untouchable things, a backdrop to our human dramas. But we are now entering an age of connection. We are beginning to understand that our solar system is not an isolated island, but is part of a vast, interconnected galactic ecosystem. Pieces of other star systems are constantly raining down upon us, and pieces of our own are constantly being flung out into the void. We are part of a great cosmic exchange. This visitor is a physical reminder that the space between the stars is not empty. It is a thoroughfare. And if messengers like 3I Atlas can make the journey from there to here, then it means that the building blocks of our world, and perhaps even of our own biology, might have made a similar journey long ago. So as we wait for the final verdict, let's hold all of these reflections in our minds. Let's appreciate this moment, not just for what it might reveal about the object itself, but for what it is revealing about us. It is a challenge to our patience, a test of our critical thinking, and an invitation to embrace the profound and beautiful uncertainty that lies at the heart of all great exploration. The initial question we asked was, is this a coincidence or a pattern? But perhaps the deeper question is, what can we learn about ourselves by watching how we grapple with a mystery that is grander than any we have ever faced before? The universe has sent us a riddle, wrapped in ice and mystery, from across the interstellar gulf. And the way we choose to solve it will say as much about our own maturity as a species as it will about the nature of our visitor. The journey of 3I Atlas is almost over. Our journey to understand it, and ourselves, is just beginning. December, a month that usually brings with it a sense of closure, of an ending year. But for those following the saga of 3I Atlas, December 2025 will feel like a beginning. It is the month of first light. After weeks of anxious silence, of staring into the blinding glare of the sun where our visitor was hidden, the orbital mechanics of our solar system will finally grant us a reprieve. The Earth will have moved far enough in its orbit that, from our perspective, 3I Atlas will emerge from the cloak of the sun. One by one, the great observatories of the world, both on the ground and in space, will be able to turn their eyes back to the traveler and ask the question that has been hanging in the air for months. What happened in the dark? The first few days of this reacquisition period will be a tense and crucial time. The initial observations will be less about grand discovery and more about a simple cosmic roll call. Is it still there? Is it a single object, or has it fragmented into a cloud of debris? Is its brightness roughly what the models predicted, or is it dramatically brighter or fainter? These first, crude measurements will be the immediate arbiters of the perihelion scenarios. If the initial reports show a faint, diffuse smudge where a bright, compact comet should be, the scientific community will know that the disintegration hypothesis has won. The story would then shift to one of cosmic archaeology, studying the wreckage to understand how and why it came apart. But if, as is hoped, the reports confirm a single healthy object, the real work will begin. The first order of business will be astrometry pinning down its exact position with the highest possible precision. By comparing this new position to the final pre-blackout measurements, astronomers will be able to make their first preliminary calculation of the non-gravitational kick. It will be the first tantalizing clue in the great natural versus exotic debate. The initial numbers will likely have large error bars, but they will set the stage for the months of detailed analysis to come. Then, the true floodgates of data will open. The James Webb Space Telescope, with its unparalleled infrared sensitivity, will once again be trained on the object. Its spectrographs will provide the definitive answer to the all-important question of the water. We will see, with unequivocal clarity, whether the post-perihelion coma is still a realm of carbon dioxide, or if it has transformed into a water-rich environment. This single observation will have the power to confirm or refute the layered nucleus model in a single stroke. Webb will also hunt for any new exotic molecules that may have been liberated from the nucleus's deeper layers by the intense solar heating, providing an even more detailed chemical fingerprint of its alien birthplace. Hubble will play its part, providing crystal-clear images in the visible and ultraviolet spectrum, allowing for a detailed analysis of the coma's structure and the behavior of the dust. And on the ground, the world's largest telescopes, from the mountains of Chile to the peaks of Hawaii, will join the campaign, bringing their own unique capabilities to bear. They will monitor the comet's brightness, its color, its polarization, building up the long-term, high-cadence data stream needed to truly understand its rotation and the behavior of its jets. This post-blackout period will also be the moment of truth for the data from Mars. While the raw data will have been on the ground for weeks, the science teams will have been working furiously to calibrate and analyze it. Now, with the new post-perihelion observations providing crucial context, the Martian data will be released to the world. We will finally see the detailed time series spectra from the flyby, the close-up look at the comet's chemistry as it was heating up. This will provide the vital before picture that will make the after picture from Webb and Hubble so much more meaningful. And what about the public narrative? This is where the story will get incredibly interesting. As the real, hard, scientific data begins to pour in, it will inevitably clash with the speculative narratives that have been allowed to grow and fester during the information vacuum of the blackout. Every new piece of data will be scrutinized, interpreted, and often misinterpreted in real time on social media. If the data points towards a completely natural explanation, there will be those who claim it's a cover-up, that the real data is being hidden. If the data reveals new and even stranger anomalies, it will be hailed as vindication by those who have been championing the exotic hypotheses all along. The scientists themselves will be in a difficult position. They will be under immense pressure to provide immediate answers, to make definitive statements based on preliminary data. But the culture of science demands caution. They will want to check and double-check their results, to eliminate every possible source of error, to write up their findings for peer review. This tension between the public's hunger for instant certainty and the scientific need for methodical rigor will be at its peak. But slowly, painstakingly, a coherent picture will begin to emerge. The initial flood of confusing, sometimes contradictory, data points will begin to coalesce around a consensus. The wilder hypotheses will be tested against the evidence, and one by one, most of them will likely be ruled out, falling away like scaffolding from a finished sculpture. What will be left, standing in the clear light of verified data, will be the true nature of 3I Atlas. It may not be the sensational, cinematic answer that some are hoping for. It may be a story of complex, nuanced, and utterly fascinating natural processes that are new to us. But it will be the truth, or at least the closest approximation of it that our current science can provide. The weeks and months after the first light in December will be a masterclass in the scientific method playing out on a global stage. It will be a time of intense excitement, of fierce debate, and ultimately of profound discovery. We will be moving from the shadowy realm of speculation into the brightly lit arena of evidence. And as that evidence accumulates, it will not only tell us the story of a visitor from another star, it will also tell us the story of our own capacity to reason, to collaborate, and to patiently, persistently, uncover the secrets of the cosmos. The quiet will be broken, not by a single dramatic announcement, but by the steady, growing hum of data, the collective voice of a planet turning its eyes to the sky, eager to learn. Let's project ourselves forward in time, beyond the initial frenzy of the post-blackout reacquisition, to a point where the dust has settled, both literally and figuratively. Let's imagine a future where the papers have been published, the debates have cooled, and a scientific consensus about the nature of 3I Atlas has finally been reached. What will our universe look like in the wake of this encounter? How will our understanding of our place in the cosmos have changed? Regardless of the final verdict, one thing is certain. Our map of the galaxy and our relationship to it will have been fundamentally and irrevocably redrawn. If the verdict is natural, but weird, this is by far the most likely outcome. Imagine that the consensus confirms that 3I Atlas is a completely natural comet, but one that is even stranger and more wonderful than we initially thought. The post-perihelion data confirms the dominance of carbon dioxide, finally proving that comets in other solar systems can be built from a completely different chemical recipe. The analysis of its trajectory shows non-gravitational accelerations that are perfectly explained by its powerful, pulsing CO2 jets. The strange visual features are all definitively shown to be elegant tricks of geometry and dust dynamics. Will this be a disappointment? Only to those who fail to grasp the profound implications of such a discovery. In this scenario, 3I Atlas becomes our Rosetta Stone for understanding planet formation elsewhere. Its chemistry provides the first hard, physical data point on the raw ingredients available in another protoplanetary disk. Its isotopic ratios, once measured, would act as a cosmic thermometer, telling us the temperature of its birthplace. It would be a tangible piece of evidence that the conditions that led to our own solar system are not universal. It would prove that the galaxy is a place of immense chemical diversity, a celestial kitchen capable of cooking up worlds in ways we are only just beginning to imagine. In this future, our models of planet formation will have to be rewritten. The very definition of what a comet can be will be expanded. Textbooks will be updated. The passage of 3I Atlas will be seen as a watershed moment, the point at which the study of extrasolar planetology moved from the remote observation of distant stars to the direct, physical analysis of their building blocks. It will inspire a new generation of missions, perhaps even a dedicated, rapid-response spacecraft designed to intercept the next interstellar visitor, to fly alongside it and study it in breathtaking detail. The legacy of 3I Atlas will not be one of alien contact, but of a deeper, more intimate contact with the natural processes of the cosmos itself. If the verdict is genuinely anomalous, now let's walk down the other path. Let's imagine that the data stubbornly refuses to fit. Imagine that the non-gravitational accelerations cannot be explained by the observed outgassing. Imagine the object performs a maneuver, however slight, that defies conventional physics. Imagine the James Webb Space Telescope detects trace elements in its coma that have no natural explanation, the spectral signature of manufactured alloys or industrial byproducts. Imagine a high-resolution radar signal from an observatory like Arecibo bounces off the nucleus and reveals a geometrically complex, non-natural shape hidden within the coma. In this scenario, the world changes. The scientific, social, and political ramifications would be almost impossible to overstate. The discovery would be the single most profound in the history of science, eclipsing Copernicus, Galileo, and Darwin. The knowledge that humanity is not alone in the universe, that another intelligence has created technology capable of traversing the interstellar gulf, would ripple through every aspect of our culture. It would ignite a new golden age of space exploration, a global effort to understand and perhaps even to respond. It would force us to confront fundamental questions about our own identity, our future, and our place within a larger, more crowded cosmic community. Of course, such a conclusion would not be reached lightly. The burden of proof would be immense. The data would be scrutinized with a level of intensity that no scientific result has ever had to endure. Every alternative, every possible natural explanation, no matter how unlikely, would have to be definitively ruled out. The process would be long, arduous, and likely fraught with controversy. But if, at the end of that process, the anomaly remains, then the legacy of 3I Atlas would be that it was the messenger, the emissary, that finally and forever answered the oldest question we have ever asked. The inevitable legacy, regardless of the outcome. But here is the crucial point. Regardless of which of these paths the future takes, the true legacy of 3I Atlas will be the journey it has taken us on. This event has served as a global, real-time stress test of our ability to handle a profound cosmic mystery. It has exposed the strengths and weaknesses of our scientific institutions, the chaotic power of our information networks, and the deep, abiding pull of the unknown on the human psyche. We will have learned invaluable lessons about how to communicate complex, uncertain science in an age of instant information. We will have developed new techniques for coordinating global observation campaigns, bringing together professional and amateur astronomers in a way that has never been done before. And we will have, as a global culture, engaged in a collective conversation about the biggest questions it is possible to ask. The new galactic map, Post-3i Atlas, will show a universe that is far more interconnected than we previously thought. The empty spaces between the stars will no longer seem quite so empty. They will be seen as pathways, as conduits for the exchange of matter and perhaps information. Our solar system will feel less like an isolated island and more like a shoreline on a vast, cosmic ocean, an ocean from which strange and wondrous things can, and do, wash ashore. And that, perhaps, is the most enduring gift of this strange visitor. It has forced us to look up, to wonder, and to think on a scale that transcends our everyday concerns. It has reminded us that we are part of a story that is immeasurably vast, ancient, and still largely unwritten. Whether it is a natural comet or something else, 3i, Atlas is a character in that story that has crossed paths with our own. And because of that encounter, our understanding of the universe and our place within it will never be quite the same. The map has been changed forever. Now, we just have to decide where we, as newly enlightened galactic citizens, are going to go next. So, we come to the end of our journey, a journey that has taken us from the cold, quiet halls of our observatories to the fiery crucible of the sun, and from the firm ground of scientific fact to the shifting mists of speculation. We have followed the trail of a silent traveler, a ghost from another star, and in doing so, we have held a mirror up to ourselves. What have we learned? And what do we do now? We began with a simple, provocative question. Is the strange synchronicity of events surrounding 3i Atlas a coincidence or a pattern? And now, after sifting through all the evidence, all the hypotheses, and all the context, the most likely and most intellectually honest answer is that it is almost certainly a coincidence. A spectacular, improbable, and narratively compelling coincidence, but a coincidence nonetheless. A universe is a vast and chaotic place. Given enough time and enough random events, patterns that seem meaningful are bound to emerge. A secret meeting of generals, a strange comet, and an observational blackout happening at the same time is not necessarily a sign of a conspiracy. It is a sign that we live in a complex world where multiple unrelated stories are constantly unfolding at once. The human brain, our magnificent pattern-matching machine, desperately wants to weave these threads into a single, coherent tapestry, a story with intent and meaning. But the truest sign of wisdom is not to force the pattern, but to have the discipline to see the separate threads for what they are, and to appreciate the beauty and the mystery in each. But the deeper question we discovered along the way is the one that will linger long after 3. Atlas has faded back into the interstellar night. What is our role in a universe that is so much stranger and more interconnected than we ever imagined? For so long, we have lived with a kind of cosmic loneliness, a quiet assumption that we are an isolated outpost of life and intelligence in a vast, sterile void. The passage of Amua Borisov, and now 3i Atlas, has shattered that illusion. They are the physical proof that our solar system is not a closed system. It is a shoreline on a galactic ocean, and things wash up on the shore. For now, what has washed up appears to be natural driftwood pieces of other worlds, shaped by the same fundamental laws of physics and chemistry that shape our own, but with a wonderfully alien twist. These messengers have brought us the gift of perspective. They have shown us that our way is not the only way, that the chemical recipe that built our home is just one of many. They have humbled us, reminding us that we are not the center of the universe, but just one of countless centers of creation scattered across the stars. This is a profound and beautiful realization. It shifts our perspective from one of cosmic solitude to one of cosmic community, even if that community is, for now, one of shared chemistry rather than shared consciousness. It means the building blocks for life, the raw ingredients we find so precious here on Earth, are likely not unique to us. They are being mixed and scattered throughout the galaxy, delivered from star to star by travelers, just like 3I Atlas. The story of life may not be a single, lonely tale written on one planet, but a great, interconnected epic, a saga of cosmic seeding and exchange that has been unfolding for billions of years. We are not the authors of this story. We are just the characters in one of its chapters, who have only just begun to read the pages that came before. So, what do we do now, standing on this new shore? We do what all great explorers have done when faced with a new and uncharted ocean. We build better ships. We learn to read the currents. We train our eyes to see what is coming from over the horizon. The passage of 3I Atlas will be a catalyst. It will spur the development of new survey telescopes, new rapid response missions, new ways of collaborating as a global community. We will get better at this. The next time a messenger arrives, we will be more prepared. We will be faster. We will be smarter. We will be ready to ask even deeper questions. And we must continue to ask the bold, and sometimes uncomfortable, what-if questions. The exotic hypotheses, even if they turn out to be wrong, serve a vital purpose. They push the boundaries of our science. They force us to test our assumptions and to collect the data that can definitively rule them out. They keep us honest and they keep us reaching. The day we stop asking, what if, is the day we stop exploring. The final gift of 3I Atlas is a renewed sense of wonder. In a world that can often feel cynical and small, this story has lifted our gaze. It has united people from every country and every walk of life in a shared sense of curiosity and awe. For a few brief months, we have all been fellow travelers, following this enigmatic object through our solar system, debating its nature and anticipating its secrets. This shared experience is a powerful reminder of what we can be when we look beyond our terrestrial squabbles and embrace our collective identity as citizens of the cosmos. The universe has not yet given us a definitive sign of other intelligences, but it has given us something almost as valuable. It has given us a series of profound and beautiful mysteries. And in the act of trying to solve them, in the patient, collaborative, and critical work of science, we find the very best of ourselves. The journey of 3I Atlas will end, but our journey, the human journey towards understanding, has no end. There will always be another shoreline, another ocean, another whisper from the void. And we will be here on this pale blue dot, waiting, watching, and ready to listen.